Hello, friends, and welcome back to the Snoozy Scientist, where we gently explore the mysteries of our world, one sleepy yawn at a time. I'm so glad you've chosen to spend a little piece of your evening, your morning, or perhaps somewhere peacefully in between, winding down with me. Tonight, we are traveling back more than 1 billion years into Earth's ancient oceans, a world before forests, before predators, before complex bodies filled the seas. This was an age that stretched across nearly 1/4 of our planet's entire history, yet almost nothing changed. It was a time scientists call the boring billion, but the truth inside it is anything but boring. For 1 billion years, life remained simple and small. Oceans were full of microscopic creatures drifting silently through ancient waters. They lived, multiplied, and survived for ages without building bodies or forming complex ecosystems. The atmosphere seemed stable, the climate calm. Nutrients and sunlight flowed through the planet, yet complexity refused to appear. Rock layers from this time stack gently across the world with almost no change. Fossils nearly vanish. Oxygen rises and then stalls for millions upon millions of years. And still, the planet holds its breath. Some scientists say this was the longest period of evolutionary stillness in the history of life, a world that paused as if waiting for something important. But what did the planet lack when it had everything life needed to grow? What force kept evolution frozen when Earth was full of possibility? How could a living world stay simple for so long and then suddenly transform afterward? And what finally ended the silence and unlocked the path to complex life? Tonight, we drift deeper into the billion-year pause, a silent chapter when the planet prepared for everything that would follow. But before we begin, if you enjoy these calm journeys through time and science, I would love it if you gently tapped like or subscribed. And if you would be so kind, tell me in the comments where you are watching from tonight and what time it is there. So now take a deep breath, let your shoulders loosen, and together let us step softly into the billion-year silence when evolution stood still. Long before the long stillness began, long before the oceans settled into their quiet rhythm, Earth had already passed through an upheaval that changed everything. The planet had once been a world of deep shadows and chemical storms, a place where oxygen barely touched the air or the sea. Then came a turning point that unfolded slowly through time. It happened not in a single moment, but across countless generations of ancient microbes. Their quiet work filled the atmosphere with a new gas, and the planet crossed into a new age. Scientists call it the Great Oxidation Event. It was not explosive or sudden. From the point of view of the early Earth, it was simply the glow of a new possibility. Oxygen seeped into the sky and into shallow seas. It rusted stone and altered the chemistry of entire oceans. The world became brighter, more reactive, more open to the idea of change. The planet after this shift felt different. The air had more breath in it. The water carried a new charge. Nutrients circulated in patterns that had not been possible before. Much of the surface was still barren rock and wind shaped by storms, yet life was already weaving itself into the world. Coastlines became places of transformation. Shallow tide pools held fragile communities of microscopic organisms that floated and clung to surfaces and built invisible networks. These were microbial worlds, and they were astonishing in their abundance. Layer upon layer, they formed carpets of life in the shallows. They captured sunlight and turned it into energy. They reshaped water and stone, leaving chemical signatures that would remain buried in rock for billions of years. Some of these microbes grew in long filaments that waved like hair in the tides. Others formed mats that covered the seafloor, thick and sticky like living blankets. From a distance, the oceans might have looked empty, but it only took a closer look to see worlds hidden in the clear blue. Every droplet of water held communities far more crowded than any modern city. Life was already restless. It experimented with new forms. A few lineages composed of more complex cells began to appear. These early eukaryotes were unlike the simpler bacteria that had ruled for eons. Their cells were larger and full of potential. They carried tiny compartments inside themselves. They could store energy and genetic information in new ways. They were like early architects holding the first sketches of bodies, tissues, and organs, even though those forms were still far away. For a moment in Earth's history, it seemed that complexity might rise quickly from these oceans. The world had oxygen. Microbes had filled every coastline. Eukaryotes had taken their first step toward a different kind of future. Then something shifted. The early promise slowed. Complexity hesitated. The world did not empty or fade. Life continued, but the experiments paused. The first eukaryotes did not disappear. They remained tucked into the coastlines and shallow waters. They drifted in the sunlit surface of the seas. They lived quiet lives in the margins where conditions were gentle and resource rich, but they did not grow larger. They did not invent new body plans. They did not make the leap into ecosystems filled with predators and prey. It was as if the world hovered at the edge of innovation, but chose not to cross that threshold. Earth at this time was stable in a way that is rare in its long history. Volcanoes still erupted, and rivers still carved through rock, but the pace of change slowed. The sky held more oxygen than ever before, yet it did not rise beyond a certain point. Seas mixed and circulated, bringing nutrients and warmth, but the deeper waters remained dark and poor in oxygen. The continents were secured in their places. Winds and waves shaped coastlines with the same rhythms for millions upon millions of years. Life adapted to that quiet. Microbial mats expanded to cover long stretches of seafloor. The first complex cells remained small and cautious. The fabric of life did not unravel or collapse. It persisted, steady and balanced. There is something almost peaceful in imagining this world, an earth where the air was gentler and the oceans were calm, where evolution took a slow breath after the great oxidation, as if testing the new conditions before taking another step. This was not the world of the Cambrian seas, or the great forests, or the thunder of dinosaurs. It was a quieter stage, the prelude to deeper transformations. The foundation was laid in silence. The ingredients for complexity existed, scattered through the oceans like seeds. Yet they waited, patient and unhurried. In the calm that followed the rise of oxygen, Earth settled into a new equilibrium. Microbial communities thrived without challenge. Early complex cells stayed small and simple. The stage was set for a different kind of change, one that did not arrive quickly or dramatically. The planet had everything it needed for life to rise again, but for reasons that were still hidden, evolution held its breath. After the world settled into its quiet foundation, a strange transformation took place. Earth had the basic pieces of a more complex future. Sunlight poured into the oceans, microbes filled every shoreline. Early complex cells had already made their first appearance. For a time, it looked as though evolution was preparing to climb upward again. Instead, it slowed, not instantly and not all at once. The shift was like the dimming of a great natural clock. The pace of change began to relax. The branches of life that had once diverged in many directions now stretched forward in long, steady lines. Entire ecosystems seemed to drift into stillness. If we look into the rock record from this age, we can see the change with surprising clarity. Layers of ancient sediments hold the memory of life. In the rocks of this time, Scientists notice something unusual. Fossils do not show the bursts of new species or sudden vanishings that are common in other eras. Instead, the patterns flatten. For millions upon millions of years, the same groups appear in the same forms. Their shapes barely shift, their presence remains constant. It is as if the world paused in one great breath. Geologists and paleobiologists describe this as reduced evolutionary turnover. It means that life was not replacing itself at the pace we see before or after. New species appeared so rarely that the fossil record seems to stretch into a long, quiet plateau. The peaks and valleys that normally mark the rise and fall of life become smooth. The graph of change almost becomes a straight line. This near flat line is not a trick of the rocks or an accident of missing evidence. It appears across many different places on Earth, from the ancient cores of Australia to the layered stones of Canada and South Africa. The same signal repeats. Sedimentary layers capture similar communities of tiny organisms for vast spans of time. These layers build and settle, one atop the next, like the pages of a book that tell the same story again and again. The stones themselves tell us that the planet entered an age of quiet repetition. In many periods of Earth's history, fossils record dramatic shifts. Volcanic events reshaped oceans. Meteor impacts cleared space for new species to rise. Climate changes created periods of sudden innovation or collapse. Yet during this long interval, those dramatic patterns fade. Catastrophes still happened, but they did not leave ripples of evolutionary upheaval. Ecosystems absorbed disturbances and returned to the same calm form. Ocean floors show this stillness in their chemistry. Thin layers of ancient mud hardened into rock, preserving microbial communities that barely changed across millions of generations. The minerals in those layers hold chemical clues that reveal slow and predictable cycles. Iron, sulfur, and carbon move through the oceans in steady rhythms. In some ancient environments, evidence of new species stops almost completely. We find stromatolites, which are layered structures created by microbial communities, continuing through this period with only minor variations. These structures appear across wide regions of Earth, shaped by similar organisms living similar lives. The world was filled with countless tiny ecosystems that looked and behaved much the same. This stability is something rare in the planet's history. Evolution normally pushes forward like a river flowing around obstacles. It branches and twists. It tries new paths. Yet in this age, the river seemed to slow into a gentle lake. The lines of change softened. Life held to what already worked. Scientists can read this slowing through subtle details in rock formations. Some layers preserve the absence of change as clearly as other layers preserve the presence of new forms. In certain cores drilled from ancient seabeds, there are no sharp boundaries or evidence of sudden transitions. The fossil record drifts in long arcs of sameness. For entire stretches of time, new innovations are absent or extremely rare. The rocks themselves become a quiet archive. Even the size and texture of sediment grains tell the story. In many places, the sands and silts that settled into ancient seas formed under gentle conditions. The absence of strong environmental pressure allowed the same microbial communities to persist. Everything about the geologic record whispers restraint and patience. When researchers analyze the microfossils from this period, they find delicate shells and tiny structures. These are the remains of plankton and other small organisms that ruled the oceans. They are beautiful and intricate, yet they remain almost identical through immense lengths of time. It is difficult to imagine this stillness repeating across continents and oceans, but the evidence is everywhere. The same story flows through stones, separated by entire hemispheres. Life continued to expand in space, but not in form. The world was full, yet it did not advance. The near flatline pattern is one of the clearest signatures of the long evolutionary pause. It is written in the thickness of rock layers, in the chemical traces preserved inside ancient sediments, and in the quiet persistence of simple life. In these stones, the earth reveals the moment when evolution slowed to a crawl, not because the planet lacked life, but because life had found a stable and enduring balance. The pace of innovation softened, the experiments of early evolution paused, time continued, yet the patterns of life moved with extraordinary calm. The world drifted into this stillness without resistance. The story of Earth entered a quieter rhythm, and the rocks became its gentle record. As Earth slipped into this long age of stillness, the oceans and coastlines settled into a world shaped by peace. It is strange to imagine an ecosystem that never heard the quiet tension between hunter and hunted. There were no sudden chases, no bodies built for speed or strength, no eyes watching from the shadows of tidal pools. This was a planet where life grew and multiplied, yet never felt the pressure that would normally change its form. Predators did not yet exist. Not a single creature fed on another in a way that required defense or escape. There were no jaws, no claws, no venom, no shells thick enough to block a bite. Every living thing survived by drifting, clinging, absorbing, or gathering food from the water around it. The oceans were full of movement, but it was gentle movement. Cells floated upward to sunlight or settled into soft mats along the sea floor. Tiny communities swayed in currents without fear. In many ways, this sounds peaceful, and in a sense it was, but peace came with a cost. When no creature hunts, there is no reason to hide, there is no need to grow thicker walls, or new senses, or complex bodies. There is no pressure to outsmart an enemy. Without the push and pull of competition between predator and prey, evolution slows. It is more than the absence of danger, it is the absence of urgency. Predation is one of the great engines of innovation. When a predator learns to swim faster, prey must learn to escape. When prey develops a new defense, predators must change too. Each side shapes the other. This endless cycle becomes an evolutionary race, and it is often this race that drives the development of new forms, new behaviors, and even new kinds of life. Without that cycle, the world followed a different path. The oceans were full of life, yet that life was simple. Microscopic organisms grew in clusters and chains. Some photosynthesized near the surface. Others fed on chemicals drifting from the deep. They expanded across the seas, but their forms remained almost unchanged. They had no reason to become more complex. They did not need faster movement or stronger bodies. The world gave them everything they needed without challenge. In the shallows, microbial mats spread across the sea floor. They grew thick and wide, like living carpets. They formed ridges and domes. They built delicate layers that recorded each passing year. But nothing came to tear them apart. No animal scraped through their surfaces or dug beneath them. They flourished the way forests might flourish if no storm ever snapped a branch and no animal ever ate a leaf. This kind of stability is rare in Earth's history. Most ecosystems in most eras are shaped by conflict and competition. Creatures evolve to outmaneuver one another. Landscapes echo with the consequences of these struggles. But during the long stillness, ecosystems were held in balance by simplicity. Imagine drifting through the ocean at this time. There would be no movement of predators hunting in packs, no sudden bursts of speed. The waters would be quiet, filled with countless tiny shapes that shimmered in the sunlight. They would absorb light or nutrients, divide and drift. It was a world where survival meant endurance rather than strategy. Even the atmosphere reflected this calm. With no rapid changes in biological communities, the gases in the air and sea shifted very slowly. Oxygen levels remained steady. Nutrient cycles moved through the oceans like slow tides. Life was everywhere, but it did not push the boundaries of possibility. The absence of predation also meant the absence of the arms race that usually speeds up evolution. No creature needed to escape, none needed to pursue. This lack of tension gave the world a particular kind of stillness, not a silence of emptiness, but a silence of equilibrium. In some places, organisms lived so densely that they created entire landscapes of their own making. They blanketed the seafloor and built reefs of ancient microbial stone, yet even here, nothing disturbed them. These ancient structures show that ecosystems grew without disruption. They spread and settled, forming shapes that lasted for millions of years. What is most striking about this time is not the absence of life, but the absence of change. The world had the ingredients for diversity. It had complex cells, sunlight, and nutrients, but without predators, the push for novelty faded. The ocean became a calm stage where life repeated familiar patterns. This was not a world of fear, it was a world of routine. It was a planet where ecosystems did not struggle or shift dramatically. The balance held firm. In this quiet earth, life grew by patience instead of competition. The oceans remained full, yet they were full of organisms that did not need to flee or fight. The world moved gently forward, guided by stability rather than conflict. Here evolution took its time, and the shape of ecosystems reflected the stillness that had settled across the planet. Long before animals filled the oceans, long before bodies grew complicated with organs and nerves and muscles, Earth's earliest life was held in place by something invisible. It was not a physical wall or a barrier in the landscape. It was a limit written into the chemistry of the planet, a limit set by energy. Everything living depends on energy. It is the quiet pulse that keeps cells alive and allows evolution to try new paths. But during this long period of stillness, the energy available to life was modest. Cells could take in enough to survive and grow, yet they could not rise into the demanding world of complexity. They were running in what we might call a low power mode. The early oceans held oxygen, but not in the amounts needed to sustain large bodies. The air above the water had changed after the planet's great oxygen shift, yet the process stopped before it could go any further. Only shallow waters received a steady supply of oxygen from sunlight and microbes. Deeper regions remained poor and slow to circulate. The atmosphere carried more oxygen than it once had, but it did not rise to the levels needed for anything beyond simple cells. Oxygen is more than a gas, it is the key that unlocks energy stored in food. It allows cells to build complex structures, to divide into many parts, to grow beyond the microscopic world. Without enough of it, organisms must conserve every bit of energy. They move slowly through their lives, dividing and drifting, repeating the simplest tasks again and again. Early cells were remarkable in their own way. They had learned how to capture energy from sunlight, how to store it, and how to keep their tiny structures functioning. Yet making a larger body is an expensive task. The cost is measured in metabolism. Building tissues requires huge amounts of energy. Every new shape or function demands more fuel. Organisms with multiple cells must feed each part. They need constant energy to keep their internal systems working. This is why multicellularity did not rise easily. It was not simply a matter of shape or genetics. It required a steady supply of oxygen that the world had not yet learned how to provide. Even though some early complex cells had appeared, they lived close to this energy ceiling. They had the tools for something greater, but they were confined by the limits of their environment. Imagine a cell floating in the prehistoric sea. Its world is bright near the surface and dark below. It divides into two, then four, then eight. Each new cell needs food and oxygen, but the ocean around it can only provide so much. If the cell tries to grow larger or become more intricate, its energy runs thin. It cannot afford to maintain more than the most basic functions, so it stays small and simple. The entire world of early life follows this pattern. The oceans of that age were full of these quiet economies. Cells lived within narrow boundaries. Their energy use was slow and careful. They spent their days absorbing sunlight or nutrients, and they devoted their strength to survival rather than innovation. In this sense, the world felt calm because life had to conserve every bit of power. There is another reason why energy held evolution in place. Complex bodies need coordination. They need to move nutrients from one cell to another. They need communication between different parts. And each of these actions demands even more energy. The metabolic cost of building even the simplest tissue is high. A single cell can only manage so much. Scientists sometimes describe this limitation by saying that oxygen was the bottleneck. It was the narrow passage that life could not pass through until conditions changed. With only modest levels of oxygen in the oceans and air, the world could support vast numbers of small organisms, but it could not support bigger ones. The energy ceiling was real and precise. This did not mean that life was weak. The ancient microbes thrived in their own way. They mastered chemical pathways, they adapted to countless environments, but they could not take the next step toward complexity because the cost was too great. Every attempt at building larger structures pushed against the limits of available energy. If the oceans had held more oxygen, evolution might have moved faster. Multicellular creatures might have appeared earlier. The world might have filled with larger forms long before it eventually did. But Earth had settled into a gentle equilibrium. The rhythms of biology matched the slow circulation of sea and air. The balance held steady. This was the world of low power mode. Life continued to expand and spread, but it did so carefully. The blueprint for complexity existed, yet it waited for the day when the planet could supply the energy needed to turn sketches into bodies. In this quiet space, evolution rested against the limits of its own fuel, and time flowed onward. In the world that followed the slow rise of oxygen and the quiet spread of early life, the oceans held on to a profound separation. They were not a single body of water moving freely from surface to seafloor. Instead, they settled into layers that rarely touched. The uppermost waters were bright and full of sunlight. Below them lay a vast darkness, cold and still, where oxygen was scarce and change came slowly. This separation is called stratification. It is the natural division of water into layers that behave like different worlds. Warm water rests above cool water. Salty water sinks below fresher water. Once these layers form, they resist mixing, and the deep oceans become locked away. For millions of years, this barrier remained in place. Imagine standing on the shore of that ancient sea. The surface ripples with life, small and delicate. The sun shines through the first few meters, illuminating tiny drifting organisms. But if you could swim into the depths, the light would fade. The world beneath would fall into shadow. The water there would be still and heavy, shaped by pressures and temperatures that remained unchanged for unimaginable spans of time. There would be little oxygen, little circulation, and little opportunity for life to become anything more than a quiet echo of the surface. This lack of mixing had deep consequences. The surface waters carried most of the oxygen and nutrients. Photosynthetic organisms near the top produced and used these resources, but what remained rarely sank to the depths. The deep ocean held its own chemistry, slow and steady. There was so little exchange between these layers that the oceans almost behaved like two separate planets sharing the same basin. When water columns stay stratified for long periods, something remarkable happens. Nutrients accumulate in the deep. They are locked away from the sunlight where they could fuel new growth. Meanwhile, the surface waters become limited. The ingredients for life do not circulate. The sea becomes stable and predictable, but also restrained. If the ocean is the heart of evolution, then mixing is its steady pulse. It moves nutrients, oxygen, and minerals across vast distances. It fuels growth and decay. It pulls carbon from the air and spreads it across the planet. When that pulse weakens, the pace of life slows. Scientists study ancient sediments and find evidence of this separation. The deep ocean left behind rocks rich in certain elements that only form when water lacks oxygen. These rocks tell us that the darkness beneath the surface stayed that way for extraordinary lengths of time. It was not a temporary lull. It was a long oceanic condition that shaped the entire world. Above this deep stillness, the surface waters reacted differently. Here, life continued to follow simple routines, as it had in earlier eras. The upper ocean had enough oxygen to support microbes and to allow early complex cells to survive. But because the deep remained isolated, the entire marine system developed without the strong circulation that could have brought nutrients to every corner. The ocean became a quiet landscape divided into layers of possibility and limitation. This stratified sea altered the course of evolution. It controlled where life could grow and how far it could spread. The boundary between oxygen-rich water and oxygen-poor depths became a barrier that few organisms could cross. The ocean, which might have been a vast, interconnected world, became instead a collection of zones. Some supported thriving communities, others remained empty chambers of darkness. For complex life, such separation carried a hidden cost. A world that does not mix cannot easily feed innovation. The nutrients that fall to the bottom after organisms die stay trapped there. Only in rare places did currents bring these nutrients back to the light. Without circulation, food chains were short and simple. Energy moved slowly through the water. Imagine that the ocean is a vast library of ingredients needed to build new forms of life. The surface shelves were skimmed again and again. The deeper shelves were untouched. Evolution was forced to use the same materials over and over, recycling what little was available. Without the deep ocean contributing its resources, there was no push toward larger bodies or more complicated structures. The lack of mixing also limited oxygen itself. The air above the water held some oxygen. The upper layers absorbed and used it, but the deep ocean remained starved. The few organisms that lived there learned to survive with very little energy. They moved slowly. They grew slowly. Their existence was bound to the chemistry around them. This quiet division between surface and depth stretched across the globe. It was visible in seas on every continent. It was written in the chemical signatures left in ancient rocks. The ocean that would not mix created a world where evolution continued, but always within strict boundaries. The sea held life like a gentle embrace, but it was an embrace that also constrained growth. For millions upon millions of years, this stratification remained. The surface and the deep watched each other from a distance, neither crossing into the other. It was a world of limited exchange and slow change, where the movement of water shaped the movement of life itself. In this divided ocean, evolution continued its quiet journey. The sea held within it the potential for something more, yet it waited, unmoving, as time flowed over it. Far below the sunlit surface of the ancient oceans, where the water stayed cold and the circulation slowed to a near stop, Another force shaped the destiny of life. It did not roar like a volcano or strike like an asteroid. It worked in silence, carried on chemical currents that drifted through the deep. The oceans had already become layered and still. Now the deep waters developed a character that would become one of the most formidable obstacles to complexity. These deep layers turned toxic. Tiny organisms near the surface created oxygen and fed entire coastal ecosystems, but the deeper ocean became filled with sulfur-rich waters. Eons of slow chemical transformation gave the lower layers a very different personality. As bacteria fed on decaying organic matter that drifted downward, they used up what little oxygen reached the depths. Then they turned to other chemical pathways. They released hydrogen sulfide, a compound that is deadly to most forms of life that need oxygen. Over long stretches of time, these poisonous waters spread and settled into the lowest parts of the global ocean. This created what scientists call a euxinic sea. The word may sound technical, but the idea is simple. Beneath the clear surface of the ocean, there was a hidden sea of poison. The water held hydrogen sulfide and lacked oxygen. It formed a boundary that few organisms could cross. The entire deep ocean became a quiet trap. Imagine the ocean as a vast bowl. The upper part is filled with life and with light. The lower part is dark and deadly, and between them lies a thin boundary where conditions shift suddenly. Only the simplest and most specialized bacteria could survive in the toxic depths. Everything else stayed close to the surface. It was not just a separation of light and dark, it was a separation of possibility. The deep ocean did not help life grow, it prevented it. This chemical divide locked the planet into a stable but unforgiving state. The surface waters held the ingredients for life, yet the deep waters captured and trapped nutrients. The hydrogen sulfide reacted with metals and minerals, creating compounds that sank and stayed buried. Every bit of organic matter that fell into the deep became part of a cycle that did not return to the surface. The ocean's heart stopped beating strongly. Its pulse weakened. In this quiet zone, life could not reach for complexity. Any form that tried to grow larger or more demanding would eventually drift too close to the toxic depths. A single mistake, a small shift in where it lived or fed, would bring it into waters that suffocated or poisoned it. The deep ocean became a constant reminder of the limits of evolution. This chemical trap was not constant everywhere at every moment. The ocean changed slowly. There were times when the toxic waters pulled back, and times when they spread again. Yet throughout the long stillness, these euxinic conditions dominated the deeper ocean. It happened in many seas across the world. It became one of the most powerful forces holding life at a simple level. We know this not just from theory, but from stone. Ancient rocks preserve the signature of these poisonous waters. When hydrogen sulfide reacts with iron, it produces minerals that settle into sediments. Over time, those sediments hardened into rock. Many of these rocks are dark, almost black, because they are filled with carbon and sulfur-bearing minerals. They are called black shales, and they are among the clearest pieces of evidence that the deep oceans were suffocating for extraordinary lengths of time. These shales appear in ancient coastlines and mountain ranges that were once the floors of ancient seas. Geologists split them open and study their layers. They see detailed records of the world that was. The chemistry tells a story of oxygen-starved depths and sulfur-rich waters. The fossils inside them, tiny and often similar from one layer to the next, reveal how life stayed simple and persistent. If the deep ocean had been rich with oxygen, evolution might have taken a different path. Nutrients would have circulated, complex forms might have found space to grow. But the presence of hydrogen sulfide created an invisible ceiling. It made the deep ocean hostile. It limited where life could go and how much energy it could use. The ocean surface remained a cradle of gentle growth. The depths remained a quiet barrier. This contrast shaped the world as surely as climate or geography. It controlled where early life could settle and how far it could evolve. The Oceanic Sea was a patient force. It did not crash into the world. It lingered. It kept the oceans calm and the pace of evolution slow. Some scientists describe these ancient waters as a trap because they held life in place. Others see them as a necessary stage, a long pause that prepared the ocean for a different future. What remains clear is that the sea itself helped maintain the billion-year stillness. The deep ocean became a realm of quiet poison. The surface held fragile communities that survived above it, and the boundary between the two became a global barrier that shaped the destiny of life. The story of these waters is written in dark rocks and ancient chemistry, a record of a world that changed slowly and held its potential in reserve. Along the ancient coasts of that quiet world, another force held the future in place. It did not come from volcanoes or storms or shifting continents. It came from the smallest forms of life. Long before forests or coral reefs, or even the first animals, the shorelines of Earth were ruled by vast microbial empires. These microbial communities built their cities from cells, sunlight, and time. They grew across the shallow seas in wide sheets and clusters. They bound sand grains together and formed gentle ridges. They shaped the coastline the way forests shape a hillside. From a distance, the water appeared calm and clear, but beneath its surface was a living architecture. Everywhere the tides reached, life covered the stone in soft mats and living films. These communities were called microbial mats. They were so successful that they dominated the coastlines for ages. A single mat could stretch across many meters and continue to rebuild itself day after day. When waves swept across them, they held firm. When sediments buried them, they rose again. They filled the shallow waters like quiet monarchs of the ancient sea. The success of these microbial mats created a world of remarkable stability. They recycled nutrients efficiently. They captured sunlight and produced oxygen. They supported entire ecosystems of smaller organisms. Because they were so good at surviving, nothing could easily replace them. They became a permanent presence along Earth's coastlines. It may seem strange that success could slow evolution, yet that is what happened. When an ecosystem works so well, there is no pressure to change it. Microbial mats did everything themselves. They produced food for whole colonies of cells. They formed protective layers that shielded the organisms within them. They responded to changing tides and shifting storms as if they had been designed for this world from the beginning. In this sense, stability became an evolutionary trap. The mats created environments that favored simplicity. Life did not need to grow larger or more complex. The mats left little space for anything new. Most organisms survived by joining them or living on their edges. Even if a new kind of organism tried to appear, there was almost no space to settle. The mats were already using the sunlight, absorbing the nutrients, and controlling the coastline. In modern oceans, coral reefs hold diversity because they create countless places to live. They build caves and branches and crevices. But in the ancient seas, microbial mats did the opposite. They flattened their world. They left little room for new shapes or bodies to emerge. The world did not move forward because it did not need to. When we look at ancient rocks from this era, we find the fossil traces of these empires. They formed layered patterns that are still visible today. Wave after wave of thin sheets stacked on top of each other. These layers show how long they persisted. They tell us that microbial mats survived almost unchanged across vast stretches of time. They even shaped the rocks beneath them. These fossils are called stromatolites. They are one of the clearest signs of how long microbial communities dominated the planet. They rise from ancient stone like soft ripples frozen in time. Their forms have changed only slightly across millions of years, a sign that evolution found a workable design and held onto it. When microbial mats spread across the coastlines, they also took control of nutrient flow. They decided how carbon and oxygen moved between the ocean and the air. They filtered sediments and shaped the chemistry of the water. They created ecosystems that favored endurance over innovation. Their dominance made the world predictable. This predictability held Earth in a long pause. The mats monopolized the resources that larger, more complex life might have used. They created an environment where change was not rewarded. In this way, their success became a barrier. The ancient coastlines were not empty, they were full, too full for anything radically new. Imagine peering into the shallow water of that time. The light shines through a clear sea. The floor beneath is covered with thick carpets of living cells. They shimmer and pulse and grow, yet they keep the world as it is. They are guardians of stability. Even deep into the stillness, microbial mats continued to thrive. They spread across every coastline they could reach. They became the foundation of entire ecosystems. And the more they succeeded, the less space remained for the experiments that evolution would later require. Life had the ingredients for change. It had oxygen and energy and early complex cells waiting in the wings. But these empires held the coastlines with gentle persistence. They had created a world that did not need anything else. So the mats remained, strong and unchanged, and the living world paused within their quiet rule. As the ancient seas settled into calm layers and microbial worlds shaped the coastlines, the land above water began its own long and patient transformation. Continents that were once scattered across the surface of the planet moved slowly toward one another. Over vast stretches of time, they collided and fused. The result of this slow and steady motion was a single giant landmass that scientists call Rodinia. Rodinia did not appear in a moment or a single event. It grew over millions upon millions of years, as smaller continents drifted with the pull of Earth's internal forces. The crust of the planet moved on plates that shifted as heat and pressure flowed beneath them. These plates carried entire forests of rock that drifted like rafts across a planetary ocean. Gradually, they merged and locked into place. The result was a world with one massive continent and vast surrounding seas. This landmass was quiet. Unlike later supercontinents that would rise with great mountain chains or break apart with explosive rifts, Rodinia formed in a gentle manner. Mountain building did happen, but it was limited. There were no towering peaks that scraped against the sky. Instead, the landscape was marked by softer hills and long plateaus. The forces that shaped it did not tear deeply into the crust or thrust giant ranges upward. It was a landscape shaped by slow collisions and subtle changes. The quiet nature of Rodinia had a deep influence on the world. Mountains are more than stone, they are sources of nutrients. When mountains rise, erosion begins. Rain and wind break down rock and carry minerals into rivers and oceans. These minerals feed ecosystems. They enrich the sea with the phosphorus and other elements that life uses to grow. When mountain building is low, erosion slows, the flow of nutrients declines. During the formation of Rodinia, the world saw very little of this process. With fewer high mountains and slower erosion, fewer nutrients washed into the sea. The rivers that flowed from this vast continent carried gentle loads. The coastlines received modest contributions of mineral-rich sediment, The oceans that touched this ancient land were calm and stable, but they were not flooded with the material that fuels complex life. In a way, the geological quiet of Rodinia echoed the biological quiet already unfolding in the oceans. The land and sea reflected each other's stillness. Just as microbial mats dominated the shallow waters and sulfur-rich depths formed a barrier in the oceans, the surface of the Earth remained locked in a long pause. The planet became a place where major geological events were restrained. The land did not rise sharply. It did not fracture violently. Everything was held in balance. This balance may seem peaceful, but it held another hidden consequence. Without large-scale erosion, the oceans lacked the nutrient-rich waters that could support complex ecosystems. Life could not easily push beyond its current limits because the resources needed for growth remained scarce. It was as if the planet itself had set strict boundaries on what evolution could attempt. Scientists learn about this ancient world by studying rocks that were once part of Rodinia. In modern times, these rocks appear in many places because the continents have drifted apart again. Yet the stones that formed during this period carry marks of a calm landscape. They show signs of shallow seas and gentle erosion. They reveal a world where sediment built slowly rather than in sudden bursts. These geological clues help us understand that Rodinia was not a dramatic continent, it was a continent of subtlety. Rodinia's presence also changed the climate. Large continents affect air and heat flow. They alter currents in the ocean. A single supercontinent can stabilize weather patterns and reduce variation across the globe. For a long stretch of Earth's past, this stability held firm. The land did not drastically change the atmosphere. The seas did not flood with new minerals. The planet turned beneath a steady sky. This was a world without the geological restlessness that drives rapid biological change. When the crust is quiet, life can become quiet too. Evolution often needs disruption. It grows quickly when conditions are uncertain, when climates shift, when oceans mix, when land rises and erodes. But Rodinia did not offer that kind of environment. It held its shape for a long time, and its calm was reflected across the Earth. The supercontinent did not remain forever. Plates drifted and forces deep in the mantle continued to move. But for the long stillness of this era, Rodinia was a symbol of patience, a world assembled slowly and kept in balance. It was a land where mountains were gentle, erosion was slow, and nutrients entered the ocean in modest amounts. The geological quiet reinforced the biological quiet. The planet was shaped by forces that moved at a careful pace. In the shadow of Rodinia, Earth became a world of long horizons and gentle change. The formation of this ancient supercontinent helped set the stage for the evolutionary calm that followed. The land itself whispered restraint, and the oceans listened. As Rodinia settled across the planet and the oceans continued their layered stillness, another quiet but powerful limitation shaped the fate of life. It was not a sudden catastrophe or a dramatic shift. It was a hunger that almost every living thing shared. It was the shortage of the ingredients that fuel growth, division, and the building of bodies. In the modern world, the oceans hold an abundance of nutrients. Rivers carry minerals from mountains. Waves break down coastlines. Sediments wash into the sea and release phosphorus and nitrogen, two of the elements that make life possible. They are not just nutrients. They are the raw material for DNA, for proteins, for every structure inside a cell. But during the long stillness of the ancient world, the shortage of these essential elements was profound. Phosphorus and nitrogen were present, but in quantities far below what the oceans would later hold. Because the land was geologically calm and mountain building was slow, erosion happened at a gentle pace. Rivers did not carry heavy loads of sediment into the sea. Rain did not grind down towering peaks because there were no towering peaks to grind. The flow of nutrients into the ocean remained limited. In a world where life already ran in low power mode, this nutrient scarcity was another quiet boundary. If the oxygen shortage kept life small, the lack of phosphorus and nitrogen kept it still. A cell might divide and drift, but it could not build large or complex forms. Multicellular organisms need nutrients not only to survive but to expand. Without a steady supply, evolution could not take the next steps. Along the coastlines, microbial mats continued to flourish because they were adapted to scarcity. They used every bit of nutrient available with great efficiency. They recycled phosphorus and nitrogen within their own small communities. They did not leave much behind for anything new to use. The deep ocean, locked away by stratified layers, held its own supply of chemicals, but they stayed isolated. The world became a closed loop, repeating the same cycles again and again. The nutrient shortage did more than limit growth. It shaped the chemistry of the ocean itself. Scientists today study ancient rocks and sediments to understand what these early waters were like. They examine the chemical fingerprints left behind by long vanished seas. In these rocks are traces of phosphorus bound to minerals, locked away in forms that could not easily feed life. Black shales, carbonate layers, and ancient riverbeds all tell the same story. The world was starved for the building blocks of complexity. Phosphorus is especially revealing. When it is abundant, new life can flourish. But when it is scarce, ecosystems slow. The geologic record shows that during this long stillness, phosphorus levels were consistently low. The ocean was not receiving enough of it from the land. The surface waters had enough to support the simplest life, but not enough to encourage something more. Nitrogen, too, was limited. Modern oceans rely on nitrogen-fixing organisms to convert atmospheric nitrogen into a usable form. These processes existed in the ancient seas, but they moved at a slow pace. With few environmental disturbances to stir the water, nitrogen remained a restricted resource. Life used what little it could find, and the ocean absorbed the rest into deep layers where it stayed. This scarcity reveals itself in the chemistry of ancient rocks. Geologists study ratios of different elements and isotopes to see how much of each nutrient was available. They find that for long stretches of time, the levels stayed low. This was not a temporary drought or a brief interruption. It was a long-term condition that kept evolution steady and restrained. Imagine a forest that receives just enough rain to survive but not enough to grow. Imagine a river that flows smoothly but never floods. The nutrient shortage created that kind of biological landscape. It held life at a steady state. Organisms survived and multiplied, but they did not find the extra resources needed to change. Even as early eukaryotes persisted in their quiet coastal environments, their growth was slowed by this underlying limitation. They had the potential to evolve into larger forms. They had the cellular machinery for complexity, but the planet did not yet provide the foundation for that growth. Rock chemistry helps us see this ancient hunger. The stones that were once mud at the bottom of quiet seas hold traces of nutrient patterns that remained constant for millions of years. They show us that the world operated on a limited budget. Every attempt to grow larger required more phosphorus and nitrogen than the oceans could supply. Life adapted to scarcity. It flowed around the limitation without breaking through. The nutrient cycles of the planet moved gently, and the world remained calm. Time continued to pass, and the oceans held their quiet balance. In that balance, the shortage became one more thread in the long pause. The earth had the pieces for something greater, but it needed more. More oxygen, more circulation, more nutrients. Until those things arrived, the great stillness held. Across the long stillness of this ancient world, the seas were calm, the land was quiet, and life moved at a gentle pace. Yet perhaps the most astonishing feature of this era was not what changed, it was what did not. For nearly 1 billion years, the climate of Earth barely shifted. Temperatures remained steady. Seasons echoed the same patterns century after century. Ice did not sweep across the continents. Heat did not surge across the oceans. The air and water continued in familiar rhythms, and the planet settled into the most stable climate it would ever know. To understand the scale of this calm, it helps to imagine the eons that came both before and after. Early in Earth's history, the planet was wild and unstable. Volcanoes erupted constantly, asteroids fell, oceans boiled and cooled. Later, the world would swing between ice ages and warm periods. Massive glaciations would freeze the seas. Tropical conditions would return. Life would be shaped by storms and shifts. But during this long quiet period, none of that happened. The world paused, the climate held a gentle balance. Surface temperatures stayed mild. Ocean currents moved slowly. Winds followed ancient paths that rarely changed. The continents under Rodinia did not drift far enough to disrupt the atmosphere. The lack of towering mountains meant that weather patterns had nothing to collide with. Storms were modest, and rainfall followed predictable courses. It is rare for a planet to find this kind of equilibrium. Earth had settled into conditions where changes were small and gradual. Even volcanic eruptions and shifting seas did not break the pattern. The planet responded with resilience. It returned to the same calm state again and again. At first, this might sound like a paradise. A world without disasters or dramatic changes seems like a safe place for life to grow. But evolution does not move fastest when conditions are comfortable. It moves fastest when conditions are challenged. Stress and variability push organisms to adapt. A sudden change forces new solutions. If a drought arrives, plants must learn to conserve water. If predators appear, prey must learn to hide. If temperatures fall, creatures must evolve insulation or new behaviors. Change creates pressure. Pressure creates innovation. But in this ancient world, the pressure was gentle. The pace of natural change was slow. The climate offered no sudden shifts or dramatic challenges. Organisms did not have to compete in a world that demanded constant adaptation. They simply continued what they already did. The stability became a quiet constraint. In modern times, scientists observe that ecosystems often grow more diverse when conditions are unpredictable. Coral reefs thrive after storms that break apart their structure. Grasslands flourish after fires that clear the old and make space for the new. Even the great mass extinctions of history open doors for new creatures to rise. Chaos creates opportunity. Yet during this long stillness, the forces that normally spark change were muted. The ocean surface stayed warm enough to support simple life. The deep remained isolated and calm. The land changed so slowly that evolution had no need to react. The global climate was like a steady heartbeat. We still see the evidence of this ancient stability in the rocks. Sedimentary layers show consistent mineral patterns. Ancient soils formed under similar conditions for long ages. The chemistry of ice cores and ocean sediments, though fragmented through time, echoes the same truth. This was a world where the climate held steady. This stability shaped everything. It allowed microbial mats to dominate coastlines. It prevented strong ocean mixing. It limited the erosion that could feed nutrients into the sea. It kept oxygen from rapidly increasing. The peaceful climate was not just a backdrop, it was a participant in the long pause. Imagine the same calm repeated through countless generations. Plants and animals today evolve quickly because every generation sees a slightly different world. But in this era, entire species lived and died in an environment that barely changed. The incentive to evolve remained weak. The world rewarded patience, not innovation. Even the atmosphere obeyed this rhythm. The balance between gases shifted only slowly. The planet found a level where the forces of heating and cooling balanced each other. There were feedbacks and loops that kept the climate from drifting far in either direction. The sun warmed the land and sea, but clouds and currents kept the temperature in check. This long period of stability did something remarkable. It preserved life as it was. It kept evolution moving forward at a slow pace. It held the world in equilibrium. And in that equilibrium, life waited, gathering the small changes that would one day allow for something more. The most stable climate Earth ever had did not push life forward. It kept it steady. It created a world where the rhythm of evolution slowed and the shape of life remained simple. The calm was complete, and time passed through it like a gentle tide. Across the long stillness of this ancient world, oxygen had already begun to change the atmosphere and the surface of the sea. Long before complex life appeared, tiny organisms near the shores and in the sunlit waters learned to split water and capture sunlight. They released oxygen as a byproduct of their quiet work. It drifted into the air and dissolved into the ocean. Slowly, it began to reshape the planet. At first, the rise was steady. The world shifted from a time when oxygen was a rare visitor to one where it became a permanent resident. The rocks from this age hold evidence of that change. Iron rusted, minerals transformed, the chemistry of the sea and sky altered under the influence of oxygen. But then, something unexpected happened. The rise slowed. The upward climb stopped. Oxygen did not disappear, but it did not continue growing at the pace one might expect. It leveled out, forming a plateau that lasted for ages. This is one of the great puzzles of Earth's ancient story. Why did oxygen rise, only to pause? Why did it not continue upward until the air resembled the world we know today? Why did the atmosphere stay steady instead of pushing further into the realm that could support larger and more complex life? One answer is found in the smallest and simplest of Earth's inhabitants. The same microbes that released oxygen also consumed it. They used it as part of their metabolism. They pulled oxygen back into chemical cycles that kept it from building up too quickly. In shallow seas and along ancient coastlines, oxygen entered the water, but microbes absorbed it as quickly as it formed. Every bit that was released became part of the delicate balance of simple ecosystems. This tug of war created a planet where oxygen levels hovered at a low but steady state. The ocean and the air worked together to maintain that balance. In the surface waters, oxygen could be produced by microbes that captured sunlight, but it did not sink freely into the depths. The oceans were layered and stratified. The deeper waters held little oxygen, and they held vast stores of reduced chemicals that reacted with it immediately. Every pulse of oxygen that drifted downward was neutralized. Hydrogen sulfide and iron-rich minerals consumed it. The deep ocean acted like a sponge. On land, the situation was similar. The rocks that weathered on Rodinia's surface absorbed oxygen. Iron in the crust reacted with it and formed oxides. The atmosphere became a participant in geological chemistry. The planet used oxygen not just as a gas, but as an ingredient in a constant cycle. The result was a world locked at a low level of oxygen, enough to support microbial communities in shallow seas, enough to create new channels of energy within cells, but not enough to allow rapid evolution or the rise of large bodies. This low oxygen state held steady for immense spans of time. It was not a brief delay or a temporary interruption. It was a stable chemical arrangement. The atmosphere reached a point where oxygen production and oxygen consumption balanced each other. The ocean and the sky formed a partnership that resisted change. The rocks tell us this story in careful detail. Scientists measure the minerals preserved in ancient sediments and see how much oxygen was available. They study isotopes of sulfur, iron, and carbon. These signatures reveal the same pattern over and over. Oxygen levels rose and then paused. The plateau became a defining feature of the ancient atmosphere. It is as if the planet had taken a breath and held it. Life needed more oxygen to move forward, but it was locked away by the chemistry of the sea and soil. Every time oxygen accumulated, the planet found ways to pull it back into balance. Microbes captured it, rocks absorbed it, the ocean neutralized it. The atmosphere refused to move out of its comfort zone. This resistance slowed the march of evolution. The amount of oxygen in the air and sea limited what life could become. Many modern innovations require high oxygen levels. Nervous systems, muscles, tissue that needs constant energy. Even the earliest multicellular organisms would have needed more oxygen than the ancient world could provide. The puzzle of the missing oxygen is not just a chemical question, it is a story about how life and environment shaped one another. It shows how the physical conditions of Earth can set boundaries on biological possibility. For a long and quiet period, this balance held. The planet had found a stable rhythm. Oxygen formed and was consumed. The cycles repeated. The world resisted rapid change. The atmosphere and ocean chemistry refused to budge, even though life was slowly transforming the surface. The balance was complete and enduring. The sky held its breath while evolution waited for the next shift. Long before the oceans would fill with animals that swam or crawled or burrowed into the seafloor, life was already trying to imagine new forms. Even in a world held in quiet balance, cells were never completely still. They divided, they searched for energy, they collided by accident, and sometimes stayed together. In these gentle attempts, the first hints of multicellularity began to appear. These experiments were small. They did not build bodies or tissues or organs. They did not sweep through the world like a sudden change. Instead, they showed up in tiny clusters of cells that had decided, for a moment, to stay attached after division. Some grew into little chains of identical units. Others formed loose colonies that drifted in the shallows. These were the first steps toward cooperation. We know this because the rocks remember. Some of the earliest fossils from this long, quiet age display the simple traces of multicellular attempts. Thin impressions and microscopic structures show colonies of cells frozen in ancient sediments. They were not complex enough to be animals, yet they were more than single cells. They were something in between, a fragile innovation waiting for the right conditions to grow. The story of these early experiments is one of potential held in place by the world around it. The cells that formed simple clusters had the beginnings of the machinery needed for multicellularity, but their tools were incomplete. They had ways to divide, but they did not yet have the systems needed to organize different roles among their cells. They could stay together, but they could not build the communication pathways that larger bodies demand. Even so, These attempts were remarkable. They show that evolution was always searching. Even in a world limited by nutrients and energy, life was feeling for new possibilities. Yet almost every one of these early steps ended in quiet failure. The attempts did not grow into complex forms. They did not leave behind lineages that led to animals or plants. They were small, simple experiments that tried to take hold in a world that was not ready for them. The reasons for these failures were not only environmental. The cells themselves had boundaries. Early eukaryotes carried structures inside their bodies that allowed them to store energy and process information. They had the building blocks for complexity, but these parts were still primitive. Their genomes did not yet contain the instructions needed to build the intricate machinery of multicellularity. Modern multicellular organisms depend on many specialized tools. They need ways for cells to communicate, to share nutrients, and to coordinate different activities. They must control when cells divide and when they stop. They must decide which cells become part of a surface and which become deeper layers. These decisions require genes that early eukaryotes did not yet have. Because the early cells lacked these tools, their attempts at forming multicellular forms were fragile. The colonies broke apart easily. They could not maintain their structure for long periods. They could not adapt to even small disturbances in their environment. A change in temperature or sunlight could dissolve them back into single cells. They did not have the stability needed to grow beyond their simple beginnings. Some of these early experiments may have relied on chance. When a cell divided and its daughter cells remained attached, the result was a temporary cluster. But without the genetic software to coordinate the group, the cluster did not become something greater. It was like building a house with walls but no beams to hold the roof. The structure simply could not stand. There is a quiet beauty in these early failures. They show that life was testing its boundaries. It was learning, cell by cell, what it could become. These attempts reveal how evolution works. It does not always move forward in steady steps. It tries many paths, and most of them fade away. The world at that time was not hostile. It was simply limiting. The oceans and air did not provide enough oxygen. The land did not supply enough nutrients. The deep sea remained toxic. And the cells themselves did not yet contain the complexity needed to form lasting multicellular forms. Even so, these early attempts at multicellularity were seeds. They show us that the idea of larger bodies was already beginning to take shape. They are hints of what life wanted to become. The fossils of these early clusters are delicate and rare, yet they tell us that the dream of complexity was already present. It simply could not rise above the quiet constraints of that ancient world. So life continued to drift and divide in its single-celled form. The ocean held these first experiments gently, as if saving the idea for later. The genetic tools for building larger bodies were not yet complete, but they were gathering. Slowly, over time, new innovations would appear. But for now, these early multicellular forms came and went like small whispers of possibilities that the earth was not yet ready to hear. Life had already taken small steps toward cooperation. It had formed tiny clusters of cells that drifted in the shallows and left faint fossils behind. The ocean held early experiments with shape and structure, yet nothing rose beyond the simplest of forms. One of the quiet reasons for this long pause was written deep inside the cells themselves. It was not a limit of water or nutrients or climate alone. It was a limit of information. Every organism carries a set of instructions that guides how it grows and what it can become. This set of instructions is the genome. It is more than a list of chemical sequences. It is a living blueprint, a pattern of memory and possibility. But in the ancient world, Genomes were small and spare. They did not yet hold the codes needed to build complex bodies. Early eukaryotes had taken an important step by developing internal compartments. They had ways of storing DNA and protecting their chemical reactions. They were one of the first organisms to carry the machinery that could support complexity. But their genetic libraries were still thin. They lacked the networks of genes that today control cell growth and communication. They lacked the switches that turn some genes on and others off. They lacked the instructions to build the scaffolding that connects cells into tissues. These limitations acted like a bottleneck. Even when the environment offered moments of possibility, the genetic tools inside the cells were not enough to seize them. A cell might divide and remain attached to its neighbors. A colony might form for a short time, but there was no way to coordinate growth or specialization. Without those instructions, the experiments could not advance. Modern organisms rely on large families of genes that handle the complex work of multicellularity. They control how cells adhere to each other, how they communicate through chemical messages, and how they differentiate into different roles. A muscle cell knows it is a muscle cell. A nerve cell knows it is a nerve cell. These decisions grow from layers of genetic regulation. Early genomes did not yet contain those systems. They held a simpler script. Innovation in biology often depends on the presence of specific molecular tools. One of the most important is the ability to build and rearrange structures called cytoskeletons. These are the frameworks that give cells their shape and allow them to move and divide. They are like internal scaffolding. Without sophisticated control of these structures, cells cannot build larger bodies. Another critical tool is the ability to communicate between cells. When organisms grow larger, cells must talk to one another. They must share signals, coordinate actions, and respond to changes in their environment. This requires a complex network of proteins and pathways. The earliest eukaryotes had only primitive versions of these tools. Their conversations were simple, their organization was limited. There is a quiet truth in the way these early genomes worked. Life was capable of imagining complexity, but not yet capable of constructing it. The genetic bottleneck held it in place. The instructions for multicellularity existed only as hints and fragments. They were seeds waiting for the right conditions to grow. We know this not only from fossils, but from modern organisms that still carry ancient patterns. Some single-celled eukaryotes living today have genes that resemble the early steps toward multicellularity. They can form temporary colonies under certain conditions. They show how close the ancient world came to taking a greater leap. But without a richer genome, those attempts remained fleeting. Scientists study the genomes of living organisms and trace their origins backward in time. They find that the complexity needed for multicellularity did not appear all at once. It grew slowly through duplication and modification of genes. It required the building of regulatory networks. It needed layers of control that early cells did not yet possess. The bottleneck was not a failure, it was simply a stage in the long story of life. Every major innovation in evolution requires a collection of parts to be in place. The machinery must be ready. The instructions must be written. The environment must allow it. During this ancient era, the machinery was only beginning to form. It could not yet support the next step. So the world remained full of single-celled life and simple colonies. The oceans continued their quiet cycles. The land remained stable. The atmosphere held its breath. Inside each cell, the genetic script slowly gathered the letters it needed, but the sentences of complexity had not yet been written. This bottleneck shows us that evolution is not only shaped by the environment outside, it is also shaped by the limits within. Early genomes held the memory of ancient life, but they did not hold the potential of the future. That potential would come later, when the world and the genes inside its living cells drifted beyond this narrow place and began to write new possibilities. Even in the most stable eras of Earth's past, quiet did not mean absolute silence. Deep beneath the calm oceans and gentle coastlines, the planet's core continued to stir. Heat moved through the mantle, pressure built beneath the crust. Every so often, that hidden energy found a path upward. The world that seemed so still from the surface would flare briefly with fire. Volcanoes did erupt during this long pause. They did not arrive as constant storms or towering mountain builders. They appeared in pulses, scattered across geological time. Each pulse left clues in the rock record. Lava cooled into basalt. Ash settled into ancient sediments. Minerals captured the chemistry of molten stone. These traces allow scientists to see through time and glimpse the volcanic heartbeat that continued beneath the stillness. These eruptions were not always large. Some were quiet flows of lava that spread across wide plains. Others were more violent, releasing gases that rose into the atmosphere. Yet even the most powerful of them did not break the world free from its long equilibrium. They were flashes of heat against a backdrop of quiet stability. When geologists study ancient rocks from this era, they find chemical markers that show these volcanic pulses. Certain isotopes of elements like strontium and neodymium shift when new rock is born from Earth's mantle. These shifts tell a story of sudden, brief events. They reflect moments when fresh material entered the crust. They mark changes in the chemistry of the oceans and the air. These signals appear again and again throughout the long pause. For a moment, these volcanic events might have seemed like the beginning of change. Fresh lava can alter landscapes. Volcanic gases can reshape climates. Ash can fertilize oceans. Yet each time, the effects faded. The eruptions did not tear apart the supercontinent. They did not release enough nutrients to break the quiet cycle of the oceans. They did not pump oxygen into the atmosphere or bring new elements into circulation fast enough to reshape life. It is tempting to imagine these volcanic pulses as sparks waiting to ignite complexity, but the world of that time was too well balanced. The chemistry of the oceans absorbed volcanic gases and minerals with little disruption. The atmosphere returned to its previous state. The deep ocean remained toxic and separated. The nutrient cycles stayed slow. Volcanoes usually bring change. They can flood the land with new minerals. They can shift climate patterns. But during this long stillness, the planet seemed to cushion their impact. The eruptions left marks in the rocks, but not in the path of evolution. Scientists find layered deposits in ancient sediments that show rapid change followed by a return to calm. Ash beds appear for a moment and are buried by quiet layers of mud. The chemistry of seawater shifts, then drifts back to its earlier state. These brief disturbances appear like short breaths in a long pause. Volcanism did not stop. It simply did not push the door of evolution forward. There is something deeply revealing about this. The planet's internal energy was still strong. The mantle still moved. The crust still cracked. But the surface world absorbed these events without transforming. It was as if Earth had found a stable configuration that resisted upheaval. The volcanic pulses also did not supply enough phosphorus or nitrogen to overcome the nutrient shortage. They did not mix the deep and shallow ocean enough to overcome stratification. They did not collapse microbial ecosystems that held the coastlines. These eruptions were moments of fire against a world that flowed back into quiet rhythms. In modern times, volcanic events often act as agents of disruption. They release gases that can warm or cool the planet. They can trigger new cycles in the ocean. They can lead to extinctions or bursts of innovation. But the ancient world was different. It was shaped by the strength of its stability more than by the force of its eruptions. The fire beneath the stillness served as a reminder that the planet was always alive with movement. Even as evolution slowed to a crawl, Earth's inner heat did not sleep. The crust shifted. Magma rose. Lava cooled into stone. These processes left their fingerprints in ancient rocks. They record brief chapters of energy and motion. The eruptions came and went, leaving a trail of clues for us to find. They show that the quiet era was not empty. It was filled with subtle activity. The world was not static. It was simply held in a balance strong enough to swallow even volcanic fire. So the lava cooled, the pulses faded, the chemical signatures settled into stone, and the surface world continued its quiet, steady path, waiting for a time when the forces beneath the crust and the life above it would finally begin to change in unison. For so long, the planet held its breath. Ocean and atmosphere, land and life, all seemed to stay within a narrow boundary of change. Across this vast stretch of time, one feature of the living world stands out as almost unbelievable. Through these ages of slow evolution and quiet seas, not a single creature could see. The earth was filled with life, yet every organism existed in a world without vision. There were no eyes watching the sunlight shimmer on the surface, no gaze lifted toward the horizon. No creature tracked the movement of another. Not even the earliest hint of a pupil or lens had appeared. This was a world without sight. At first, the idea feels strange. Light poured into the surface waters every day. The sun rose and fell, painting the ocean in colors and warmth. Yet nothing living had the ability to sense it beyond the simplest reactions. Some organisms could tell when light was present or absent. They could drift toward the brightness or away from it. But they could not form images. They could not detect shapes or motion. They had no way to interpret the dance of photons that filled their world. Vision is one of the most powerful evolutionary innovations. It allows organisms to understand distance and depth. It turns the world into patterns. It gives animals the ability to find food, escape danger, and explore their environments. But during this long stillness, the world had not yet created the tools for sight. The leap from simple light detection to true vision is enormous. It requires far more than a single change. It demands complex cellular machinery. It demands proteins that can capture light and convert it into signals. It demands nervous systems that can interpret those signals. It demands the development of cells specialized for direction and focus. In the ancient seas, these ingredients did not yet exist in the same organism. The early eukaryotes that experimented with multicellularity did not have the genetic networks required to build eyes. They lacked the proteins that respond to specific wavelengths. They lacked the communication systems needed to link cells together into sensory tissues. The machinery of sight was still scattered across evolution, waiting to be assembled. Instead, most organisms navigated the ocean by chemical signals alone. They sensed nutrients in the water. They responded to changes in pressure or temperature. They drifted with currents rather than chasing or fleeing. The sea was shaped by touch and chemistry rather than by sight. Because no creature could see, the need for vision never arose. Predators did not exist. Prey did not need to detect movement. The arms race that would one day drive the evolution of complex eyes had not begun. This absence of predator and prey relationships meant that organisms did not need to evolve rapid responses to sudden threats. They lived in a world where everything moved slowly and with purpose. Darkness shaped the ecosystems of this age. Even in the sunlit shallows, the absence of eyes meant that light did not have the same meaning it would later hold. The surface and deep waters formed different worlds, not because of vision, but because of chemistry. The creatures that lived in the upper layers did not use sight to find food or shelter. They relied on chance encounters. In the deep ocean, where sunlight could not reach at all, life moved in total darkness. These depths were ruled by chemical gradients and subtle flows. The absence of light did not change much here because nothing relied on light in the first place. The world below was a realm of quiet sensation without shape or form. When we think of modern oceans, they are filled with eyes. Fish navigate by vision. Jellyfish pulse through the water with light-sensing organs. Plankton shimmer and flash. Even tiny creatures detect changes in brightness and movement. But during this long pause in evolution, the oceans were far simpler. The creatures that lived there experienced the world without images or colors. This lack of eyes was not a failure. It was a reflection of what the world needed at the time. Evolution does not create organs because they are possible. It creates organs because the environment demands them. Vision is costly. It requires energy and coordination and complex biology. In a world without competition or fast changes, vision brought no advantage. The pressure to evolve eyes simply did not exist. The absence of vision helped maintain the slow pace of change. Eyes would have introduced new behaviors. They would have allowed some organisms to find food more quickly or avoid danger more effectively. They would have created imbalance. But the world of this era floated in equilibrium. The darkness did not harm life. It shaped its rhythm. It made the ocean a place of drifting and calm. It allowed the earliest organisms to explore other aspects of survival long before sight ever appeared. So for 1 billion years, the world saw no eyes. The sun rose and fell, the ocean sparkled and shone, yet no creature watched. Life continued through the long stillness, feeling its way forward in the quiet dark, holding the idea of vision in reserve for another time. Across the long stillness, life was not idle. It drifted, divided, experimented, and survived. It filled the shallow seas and coated the edges of ancient continents. Yet it did not advance into complexity. Each attempt at change faded against the same set of boundaries. It is almost as if the planet itself was not withholding complexity, but waiting for something. There are moments in Earth's story when progress depends on thresholds. These thresholds are like invisible gates. Life can move up to them, but cannot cross without certain conditions in place. For complexity to rise, these gates must open in a particular order. Each one needs time and chemistry and the right balance of chance and necessity. During this long pause, the gates were still closed. The first gate is energy. Complex organisms require more than a trickle of power. They need abundant oxygen and efficient metabolism. They need machinery inside their cells that can produce energy at high rates. But the ocean still held deep layers with little oxygen. The surface waters had enough for microbial life, but not enough for creatures that would require larger bodies. The second gate is nutrients. Phosphorus and nitrogen must circulate freely. They must move from land to sea and back again. These elements feed the growth of tissues and shape the architecture of life. But the ancient world was geologically calm. Weathering was slow. Rivers carried gentle loads, and the nutrient cycles remained limited. The third gate is genetic. Cells need more than the ability to divide. They need the instructions for coordinating many parts. They need genes that control growth and specialization. They need systems for sending signals and sharing resources. The early genomes held only glimpses of these possibilities, not the full orchestration needed for complexity. The fourth gate involves the world around life. Environments must change enough to encourage innovation. Climate must shift. Predators and prey must co-evolve. Organisms must face challenges that push them to adapt. But the climate during this era was the most stable Earth ever had. It offered peace instead of competition. It did not create the pressures that drive rapid evolution. It was not that life was failing. It was simply that the gates were not yet aligned. Scientists sometimes think of these gates as thresholds of possibility. When conditions fall below the threshold, innovation slows. When conditions rise above it, evolution moves quickly. But during this long stillness, many of these thresholds hovered just below their tipping points. Oxygen rose, then paused. Nutrients gathered, then became trapped. Cells developed new tools, but lacked the energy or resources to use them. The planet did not resist complexity. It simply did not yet contain the full combination of requirements. This is one of the most intriguing features of Earth's history. Complexity did not emerge the moment it became possible. It waited. The world needed more oxygen in the deep ocean, more nutrient circulation, more genetic machinery. It needed volcanic activity to shift the chemistry of the atmosphere, but not too quickly. It needed the land to change in ways that would release minerals into the sea. It needed the right kind of disruption. Across the quiet seas and the calm landmass of Rodinia, these thresholds remained just out of reach. Microbes could push against them. They could build colonies and form cooperative clusters. But the world around them did not yet offer the rest of the ingredients. Even when volcanic pulses erupted, the effects did not last. Even when early cells tried to form simple bodies, they lacked the instructions. Even when oxygen formed in the surface waters, the deep ocean consumed it. Each gate opened a little, then closed again. It is almost as if Earth was preparing the scene, like a vast stage waiting for the next act. The concept of evolutionary gates teaches us something profound. Evolution is not just about adaptation and mutation, it is about timing. It is about the whole planet moving together through cycles of change. It is about many separate conditions aligning, each one shaping the others. Why did it take so long for these thresholds to be crossed? Because Earth was still settling into itself. It was transforming from a world shaped by chemical reactions into a world shaped by ecosystems. It was moving from simplicity to structure. These transitions require stability and disturbance in delicate balance. They require patience measured not in millions of years, but in billions. During this quiet era, the planet drew closer to the gates. Oxygen accumulated slowly. Nutrients began to shift. Early genomes expanded, but the forces that would push life beyond those limits had not yet gathered. So the Earth continued on its path. The ocean surface reflected sunlight. The continents held their shape. The deep waters remained dark. And the thresholds that would one day open the way for complexity waited in silence, held in place by the slow rhythms of a patient planet. Even during the long stillness, the planet was never frozen in time. It only seemed that way when we look at the world from a great distance. If we step closer into that ancient age, into the quiet waters and gentle skies, we find that change was always flowing beneath the surface. It did not come in sudden storms or violent upheavals. It came as a slow accumulation of forces that grew until they began to reshape the earth. Pressure was building, and the signs of it were subtle. The first hints appeared in the sea. The layers of the ocean did not remain as perfectly balanced as they once had. Tiny shifts in temperature and salinity began to alter water movement. The surface waters still held most of the oxygen, but small pockets of the deep became less hostile. Currents stirred more often, and some of the nutrients that were trapped below drifted upward. These changes were slight, almost invisible compared to the dramatic events that would come later in Earth's history. Yet, they mattered. The ocean began to breathe a little more deeply. The quiet circulation of water made more room for life near the surface. On the land, Rodinia was not perfectly still either. Though it was a peaceful supercontinent, parts of its shape shifted. Some regions rose slowly, others sank. The crust stretched in places where it had once held firm. These movements were not the kind that built towering mountains. They were small adjustments, like the creaking of ancient stone. Yet they changed how rivers flowed and where nutrients traveled. Each river carried tiny fragments of rock into the sea. Each shift in land changed the chemistry of the oceans below. Weathering continued its slow work. The land and water exchanged minerals in cycles so long and gentle that no creature living then would have noticed. But over millions of years, these subtle changes began to add up. In some places, volcanic activity introduced new minerals into the sea. Even if the eruptions did not cause sudden change, they contributed to the slow movement of elements that life needed. Here and there, new deposits of phosphorus found their way into coastal waters. The ocean's surface, once so limited, held pockets where life could grow slightly more abundant. These small differences did not break the stillness. They did not immediately lead to complex forms. Yet the balance was shifting. The world had not forgotten how to move. It was just taking its time. The atmosphere, too, began to change in ways that were almost imperceptible. Oxygen levels crept upward with slow persistence. They did not rise in vast leaps. They did not flood the air in sudden bursts. Instead, they increased in quiet increments. The same microbes that once consumed oxygen as quickly as it formed began to encounter slightly different conditions. Some coastal regions allowed oxygen to linger longer. Certain shallow seas became more efficient at storing it. The deep ocean did not stay entirely unbreathing. Tiny channels of circulation brought small amounts of oxygen downward, changing the chemistry of the deep. Scientists can see this transition in ancient rocks. The minerals show a faint but unmistakable shift. The world was slowly becoming more oxidized. Iron and sediments began to change into forms that require more oxygen. Sulfur left different signatures. These chemical traces are like whispers in the stone. They tell us that the atmosphere was no longer locked into its old equilibrium. Even tiny increases in oxygen began to nudge evolution. Some organisms found it easier to produce energy. Small increases in metabolism allowed for slightly larger cells, slightly more complexity, slightly more experimentation. Life could not yet make the leap into multicellularity, but it could move closer to that threshold. The water, the land, and the air all participated in these quiet changes. Nutrient cycles became slightly more efficient. Weathering delivered minerals a little faster. The ocean absorbed and redistributed elements in new patterns. Every part of the planet felt the adjusting of forces that had once held it still. These changes did not announce themselves. They crept through the world like slow tides. There was no sound of breaking stone or sudden shift in the sky, but a quiet tension built across the earth. The balance that had defined the ancient world began to loosen. The long pause that held life steady was not ending yet, but it was moving. Even the creatures living through this time were part of the subtle transformation. Microbes continued to shape the chemistry of the sea. Eukaryotes continued to expand their genetic libraries. Each small mutation, each slight adaptation, added to the potential that would eventually break the long equilibrium. It is easy to imagine this age as static, but the truth is more delicate. The stillness was not a rigid wall. It was a moment when change was measured in whispers instead of storms. The forces that held evolution in place were beginning to shift from beneath. The planet was gathering the conditions it needed. It was preparing, quietly and patiently, for what would come later. The world was still, yet not silent. The pieces of change were slowly aligning. The earth was waiting, and the pressure building beneath the calm was the first sign that the long stillness would not last forever. In the quiet surface waters, where sunlight touched the planet every morning, life was still simple. But something new began to unfold there, and it unfolded slowly, as if the ocean was testing each new step. The first signs of real change did not come from storms, from eruptions, or from shifting continents. They came from the tiniest forms of life. They came from algae. For a long stretch, these photosynthetic organisms had been content to live much as they always had. They floated gently. They absorbed light. They formed thin green drifts that gathered near the shore and spread out into the open sea. But then, over long spans of time, their numbers began to increase. Their shapes began to diversify. Small variations in their structure allowed them to live in slightly different environments. Some lived closer to the surface. Some settled deeper in the water where the light was weaker. Some took on new ways of capturing energy. These changes were not visible on a single day or even over a lifetime. They built up the way tiny grains of sand build a shoreline, yet the effects were extraordinary. A slow bloom of algae began to spread through the oceans. It made the surface waters richer and more active than before. It created layers of drifting green that shifted with the tides. With this expansion of algae came a change in chemistry. When these organisms captured sunlight, they produced oxygen. Much of this oxygen dissolved in the shallow water, where it had always stayed. But now, with more algae and more photosynthesis, small amounts began to travel downward. The water no longer held the same strict boundaries between oxygen and darkness. For millions of years, the deep ocean had been nearly untouched by oxygen. It had been a place cut off from the surface world. It was filled with minerals that reacted instantly with any oxygen that entered. Yet as conditions changed, small pockets of deep water began to feel the presence of oxygen for the first time in ages. These deep water oxygenation events were brief at first. They appeared in narrow regions of the sea. They disappeared when currents shifted. But they did something important. They began to slowly oxidize the deep ocean. If oxygen is like fire in the air, it is like a slow breath in the sea. It opens the door to new kinds of metabolism. It allows organisms to produce more energy. And in this ancient world, energy was the most precious resource. Even small increases in oxygen allowed some cells to run their chemistry faster, to divide more quickly, and to store more information inside themselves. Life had struggled for ages in an environment that limited every step forward. Now, tiny changes were lifting those limits. The deep waters also began to release nutrients that had been locked away. When oxygen entered these places, it changed the chemistry of the sediments. Phosphorus and other elements that had been trapped for millions of years started to dissolve into the water again. Currents carried them upward. Along the coasts, rivers delivered fresh minerals from the land. The ocean surface suddenly had more of the ingredients it needed to support growth. The algae responded. They grew in more shapes and sizes. They spread farther across the surface. They became more efficient at capturing sunlight. Their diversity created new opportunities for other organisms. Some microbes evolved ways to feed on them. Some began to interact in small networks. These tiny relationships marked the first steps toward ecosystems that were more complex than anything the ocean had seen before. This shift was quiet, as everything had been, but it was a powerful change. Algae played a role that would echo through the future. They continued to draw carbon from the air and produce oxygen. They continued to push oxygen into deeper waters each time currents pulled the surface downward. Over time, the ocean became less isolated. The boundary between shallow light and deep darkness became more open. We see the evidence of these events preserved in ancient rocks. Layers that once showed no oxygen suddenly display minerals that could only form in its presence. The isotopes of certain elements change as the deep ocean begins to breathe. These marks are not uniform. They appear in separate places at separate times. But together, they show that the ocean was slowly awakening. These tiny shifts created a foundation for everything that would come later. The world did not leap forward. It stepped carefully. It built potential grain by grain, cell by cell. The new algae did not transform life overnight. They changed the planet in the smallest ways. They altered chemistry. They expanded metabolism. They created small disruptions in a world that had known only stillness. The deep water did not become fully oxygenated yet. It would take much longer for that to happen. But the direction had changed. The threshold that once held life in place was beginning to soften. The energy that life needed was arriving in small surges. The oceans were growing more dynamic, and the planet, still quiet on the surface, was moving closer to the moment when complexity could finally rise from the depths. As small changes gathered in the oceans, the calm world that had held life steady for so long began to shift in ways that were almost invisible. The first signs of change were not large animals or complex bodies. They were subtle shifts within the smallest forms of life. New microbes began to appear, and they arrived not as a sudden wave but as gradual newcomers in an ancient community. For countless ages, the oceans had been shaped by stable networks of simple organisms. They drifted in gentle currents and clung to rocks along the shores. They formed vast blankets on the seabed and glided through the water column. These communities had been successful for a long time. They had shaped the chemistry of the sea and the atmosphere. They had monopolized nutrients and energy. But as the oceans received tiny amounts of extra oxygen and nutrients, the balance began to change. Certain groups of microbes found slightly new ways to use these resources. Some developed more efficient ways to capture energy from sunlight. Others discovered methods of extracting nutrients from places that had once been difficult to reach. These small innovations gave them an advantage. An advantage is one of the great engines of evolution. The old microbial communities were no longer alone. New competitors arrived, bringing new biological strategies. They grew faster in some waters. They spread more easily across certain regions. They colonized small pockets of the ocean that had once been empty or underused. This was the beginning of competition. Until now, life had been content to share the ocean with little need to defend territory or fight for resources. The world had been rich enough in its own slow way, but competition changes everything. When two organisms need the same resources, the one that can gather them more effectively often thrives, and when one thrives, the others must adapt or move aside. These new microbial competitors created a slow disruption in ancient ecosystems. The balance that had lasted for millions of years began to shift. New species emerged, not through sudden leaps, but through countless small variations. Cells that could absorb light at different wavelengths, cells that could survive in slightly more oxygenated waters, cells that could move more efficiently or divide more quickly. With these changes came the first hints of ecological organization. Some microbes fed on the waste of others. Some took the oxygen produced by their neighbors and used it to drive their own metabolism. New food webs began to take shape, though they were still microscopic and delicate. The ocean was no longer a single community. It was becoming a mosaic of habitats and interactions. Competition is often viewed as a struggle, but in evolution, it is also an opportunity. It forces life to explore new options. It encourages diversity. It pushes organisms to develop new tools. The slightest advantage can lead to great innovation over time. In this ancient world, even the tiniest shifts in competitive balance carried great potential. Scientists studying ancient rock layers find evidence of these changes in the chemical signals left behind. Certain types of isotopes appear where they were once absent. Fossils of microbial colonies show new branching patterns and structures that were not present before. These clues reveal that the ocean was becoming more complex even before visible organisms evolved. Competition also led to the first ecological disruptions. Some microbial communities expanded rapidly, crowding out their neighbors. Others declined in population. The old structures of life began to loosen. This was not a sudden collapse. It was more like a gentle rearrangement, but it was enough to alter the flow of energy in the ocean. Microbes that had once been dominant started to lose ground. Algae that captured sunlight in more efficient ways became more common. New species of bacteria evolved to take advantage of the shifting conditions. The slow and steady world was beginning to change from within. These changes introduced a new kind of biological dynamism. Even without larger organisms, the ocean was developing more layers of complexity. The presence of competitors encouraged organisms to expand into new environments. Some microbes moved into deeper water where oxygen was becoming more available. Some stayed near the surface where light was strongest. Others adapted to survive in more extreme conditions. For the first time, life was not just persisting, it was beginning to explore possibilities. This rise of new microbial competitors did not mark the arrival of complex life. That transformation was still far away, but it did show that the ocean was capable of change. It showed that life would not stay simple forever. The ancient equilibrium had been nudged. The stable world of the long stillness was still quiet, but it was no longer uniform. Competition did not overturn the world. It opened pathways. It created gradients of opportunity. It reshaped relationships between organisms. These shifts were the first steps toward ecosystems that were more intricate and dynamic. In the deep time of Earth's history, complexity often begins with small steps. It begins with organisms that learn to share space in new ways, with communities that shift and reorganize, with competitors that find ways to survive where others cannot. The ocean was changing, its patterns were becoming richer. The stillness remained on the surface, but beneath it, life was beginning to move. For ages, the world had been held in a kind of balance. The oceans breathed slowly. The climate drifted in gentle rhythms. The land masses sat together in the great supercontinent we call Rodinia. It was a still world on the surface, as if locked in a peaceful pose, but no continent remains unbroken forever. Even the quietest eras carry the seeds of movement deep within. Beneath the crust, heat continued to rise from Earth's core. The mantle stirred, the plates pressed together. Some slipped past, some pulled apart, some buckled under pressure. These movements were slow, but they were relentless. Over immense stretches of time, the tension inside the planet grew. The supercontinent began to feel that pressure. Rodinia did not break suddenly, it stretched first. Fissures formed slowly across its surface. Some regions sagged downward, others rose. What had once been a single great landmass started to divide. Cracks spread across the rock, the surface became fractured with rift valleys. Lava welled up from below as ocean water began to seep into these openings. This process of rifting released the world from part of its stillness. When land splits apart, it does more than reshape the map. It awakens deep cycles that have been waiting. Magma rose from the mantle, cooling into new rock. Volcanic eruptions became more common along these rift zones. Each eruption sent minerals into the air and into the sea. These volcanic events were different from the quiet pulses we have seen before. They were part of a growing pattern. The breakdown of Rodinia increased volcanism. The earth was changing from its deep foundation. With every eruption, the land delivered more nutrients to the ocean. Basalt and ash carried phosphorus and trace elements that the sea had long lacked. Rivers flowed across new surfaces, carving minerals into their bedrock and carrying them outward. This fresh supply of nutrients began to feed the ocean in ways it had not experienced during the long stillness. The circulating minerals awakened ancient cycles of productivity. The deep ocean was still not fully oxygenated, but the balance was shifting. More nutrients meant more algae. More algae meant more oxygen. The changes were slow, but they were constant. As Rodinia continued to separate, new coastlines formed. These coastlines were not static. They moved with the land. They created new shallow seas, rich with sunlight and minerals. These shallow waters were some of the most fertile environments of the ancient world. Here, life could expand. Here, the calm equilibrium began to loosen. Continents breaking apart also changed the weather. Winds and rain patterns shifted. Regions that had once been dry became wetter. Rivers found new paths. The increased rainfall helped break down rock, sending minerals into the sea more quickly. The long drought of nutrients that had held back evolution was being replaced by a slow but steady flood. It was not a single moment of transformation. It was a gradual unlocking. The ancient cycles that feed life were waking. The earth was beginning to move again, both above and below. The energy stored in its interior was changing the chemistry of the sea and the air. Even the deep ocean felt this shift as oxygen trickled into places that had been starved of it. Scientists today can trace these changes in the rocks. They find evidence of rifting, volcanic deposits, and the new minerals carried into the sea. They see chemical signatures that indicate increased productivity in the surface waters. The signs are subtle, but unmistakable. The breaking apart of Rodinia did more than reshape geography. It created a feedback loop. More volcanism meant more nutrients. More nutrients meant more biological activity. More biological activity meant more oxygen. The ocean and atmosphere began to change in response. The slow world that had held evolution in place for so long was beginning to move toward a different future. Even the deep circulation patterns of water began to shift as new ocean basins opened. Water moved through these basins differently. The stratified layers that once kept oxygen out of the deep began to mix more easily. These changes were small, but they built upon themselves. The planet's cycles were awakening. The world that had been held in equilibrium was loosening its grip. Rodinia's rifting allowed Earth's interior to speak again through molten rock and mineral-rich water. It reminded the sea that change is part of the planet's nature. As the supercontinent slowly divided, it set into motion the first steps that would eventually lead to a very different world. The long stillness was not over yet, but the spell had been broken. The land was moving. The ocean was stirring. The quiet balance that held evolution steady was beginning to shift, carried forward by heat from the core and the slow splitting of ancient stone. For almost 1 billion years, the oceans held their secrets beneath layers of stillness. The surface glimmered with sunlight and life, yet the deep remained closed to oxygen. It was a realm ruled by ancient chemistry. Minerals soaked up every bit of oxygen that managed to drift downward. Hydrogen sulfide lingered in the dark. Iron-rich waters swallowed new molecules as soon as they appeared. The ocean had been divided into two worlds. Above, shallow seas breathed gently. Below, the depths were quiet and untouched. For ages, this pattern held. But as the continents began to shift and rivers carried fresh minerals into the sea, something subtle started to change. The ocean began to circulate a little more. Pockets of oxygen were pulled into deeper places. The boundary between light and dark began to soften. Then, slowly and almost without announcement, oxygen finally slipped into the deep. This moment did not happen in a single place or at a single time. It happened in pulses. Small currents brought oxygenated water down into the depths. Volcanic rifting introduced minerals that changed the ocean's chemistry. Algae blooms sent oxygen into the sea in greater amounts. These influences came together and pushed the ancient balance away from its long equilibrium. At first, the deep ocean resisted. It was filled with compounds that reacted immediately with oxygen. Iron turned to rust. Minerals changed their form. Hydrogen sulfide was consumed by simple chemical reactions, but with each small pulse, a little more oxygen remained. The ocean began to transform, grain by grain, molecule by molecule. Scientists today can see the evidence of this change in the rocks. They study the isotopes of elements such as uranium and molybdenum. These elements react differently depending on how much oxygen is present in the water. When the deep ocean holds no oxygen, they form one kind of mineral. When oxygen reaches into the depths, they form another. The ratios of these isotopes are like messages from the ancient sea. In rocks that formed during this time, the isotopic signatures begin to shift. They show that the deep ocean was no longer sealed away from the surface. They reveal moments when oxygen reached places it had not touched in millions of years. These patterns appear in many places across the world, which tells us that this was not a local event. It was a global change. The Earth was beginning to breathe more deeply. When oxygen enters the depths, it changes everything. It alters how nutrients move through the sea. It changes which organisms can survive. It opens the door to new metabolism and new forms of life. Oxygen allows cells to release far more energy from the molecules they consume. With more energy, evolution gains room to grow. Before this moment, the deep ocean had been a chemical trap. It held vast stores of nutrients in forms that life could not easily use. Phosphorus fell to the seafloor and stayed there. Iron reacted with sulfide and sank into sediments. These nutrients were locked away, but when oxygen entered the deep, these elements began to circulate again. Phosphorus dissolved into the water. Iron changed into forms that could rise upward. The cycles that feed life grew more active. The ocean was still not a world filled with large animals. It was still the realm of cells too small to see. But the chemistry of these waters began to favor innovation. Metabolisms that once ran in low power began to accelerate. Competition increased in the depths. New strategies for survival emerged. The slow separation between surface and deep started to weaken. This did not lead to a complete transformation yet, but it marked a turning point. The deep ocean had finally become part of the living system of the planet. The arrival of oxygen in the deep also affected the atmosphere. When oxygen reacts with the ocean, It changes the balance of gases above the water. It allows the air to hold more oxygen for longer. The great cycles that shape life and climate became more connected. The planet shifted into a different mode, one where the surface and deep communicated more freely. We can imagine this moment not as a sudden rush, but as a gradual opening. The deep ocean became less toxic. Its waters began to mix with the surface. The minerals that had been locked away for so long were released, one by one. The old boundaries that held life in place began to dissolve. This was one of the most important chemical changes in the history of the planet. Without oxygen entering the deep, the ocean could not have supported more complex organisms. Without this shift, the energy needed for multicellular bodies would have remained out of reach. The ocean would have stayed a realm of simple cells and slow processes. Instead, oxygen slipped into the deep, and the world began to change. The great breathing of the sea had finally begun, with oxygen finding its way into deeper waters and nutrients moving more freely through the sea. A quiet transformation began within the cells that lived near the surface. For millions of years, algae had drifted and multiplied as simple forms. They captured sunlight and turned it into chemical energy. They helped shape the atmosphere and supported the earliest food webs. But now something new was emerging from these familiar organisms. Their cells were beginning to change from within. To understand this shift, we must step into the inner world of a eukaryotic cell. Eukaryotes were not like the simpler bacteria that had dominated the planet for so long. They carried their DNA in protected compartments. They possessed tiny structures that helped them store energy and organize their chemical reactions. These features had always made them different, but during this period, these differences began to grow more important. One of the most important innovations was the ability to produce energy more efficiently. Inside these cells were mitochondria, small structures that took in simple molecules and used oxygen to release much more energy than earlier cells could create. As oxygen levels rose, even in small amounts, mitochondria became more powerful. They did not just allow cells to survive, they allowed cells to do more. This extra energy meant that some algae could begin to expand. Their cells grew larger. Their internal machinery became more complex. They could divide in new ways and build more sophisticated structures. They could store energy for longer periods and use it to explore new strategies. These changes did not happen quickly. They happened slowly, like a careful unfolding. At the same time, many algae carried another powerful tool. They contained chloroplasts, the structures that capture sunlight and turn it into food. Chloroplasts also became more efficient during this period. They developed new pigments and new chemical pathways. They learned to survive in slightly deeper waters and to make use of light that other organisms could not. Together, these two innovations, mitochondria and chloroplasts, created cells that were unlike anything that had existed before. They had ways to gather energy from both sunlight and oxygen. They could weave these sources of power together in delicate patterns. With this extra energy, the cells became more flexible. They could divide more rapidly. They could survive longer in difficult conditions. They could compete with older forms of life. This was the slow birth of complex algae. These algae began to branch into new forms. Some grew into long chains that floated in the open sea. Others became broader, allowing more sunlight to reach their chloroplasts. Some developed shells or protective coatings. Each adaptation was a small step, but over millions of years, these steps built a foundation for complexity. New varieties of algae began to settle in different environments. Some lived closer to the surface, where sunlight was strongest. Some drifted deeper into the water column where oxygen was just beginning to appear. Others found space along the coastlines where waves and tides brought nutrients in regular cycles. These subtle differences created more ecological niches. More niches meant more opportunities for evolution. Algae became more diverse in form and function. They began to shape the ocean in ways that were more dynamic than before. They changed how sunlight entered the sea and how nutrients moved from place to place. They became the architects of new ecosystems. Scientists look to ancient rocks for evidence of these changes. In fossils known as acritarchs, we can see the earliest hints of complex algae. These fossils are tiny, but they carry intricate patterns. Some show spines and ridges. Others display layered walls that protected the cell within. These features were not simple. They were the result of new cellular tools and new genetic instructions. These innovations may seem small, but they were a turning point in life's history. Complex algae were among the first organisms to take advantage of increased oxygen and nutrients. They were among the first to use new cellular machinery to build more elaborate structures. They were among the first to explore complexity. These changes set the stage for much larger transformations that would come later. The ocean was now filled with organisms that could do more than simply survive. They could respond to their environment. They could outcompete each other. They could evolve into new forms. They could become the ancestors of plants and countless other lineages. In the vast and ancient world of the sea, these new algae drifted and spread. They did not transform the planet in a single moment. They did it slowly, as the Earth always does. Their presence marked a new chapter in the story of life. For the first time, complexity was rising from within. The oceans were becoming richer in possibility, and the gentle shift that began within these cells would eventually change the destiny of every creature that followed. The continents had been shifting and opening for ages. Cracks in the crust widened into young ocean basins. Mountains rose and faded. Rain fell across newly exposed rock. Slow, unhurried weathering began carving minerals away and sending them on long journeys toward the sea. Once, for countless millions of years, the oceans had been starved of certain elements. Phosphorus and nitrogen, the nutrients that fuel the growth of large and complex organisms, were scarce. Rivers had carried only small amounts of them. Land surfaces had been low and ancient, worn smooth by uncounted generations of wind and water. There was little soil to wash away. There were few storms powerful enough to free these hidden minerals. But now the world was changing. Tectonic movements had opened new coastlines and exposed fresh rock. These rocks were rich in the very minerals the oceans had long been missing. Rainwater dissolved them grain by grain, atom by atom. Each drop picked up phosphorus and iron and carried them toward the rivers. The rivers, in turn, delivered this gift to the sea. These nutrient surges did not arrive suddenly. They came in pulses and waves. They arrived after long periods of quiet, when the land had been reshaped by mountain building or when volcanic ash had settled across a landscape. Each time it happened, the oceans responded with life. In shallow waters, algae grew thicker and richer. They gathered sunlight and turned it into chemical energy with greater ease. They built new pigments to take advantage of changing conditions. They multiplied faster. They drifted farther. They reached deeper. These storms of nutrients changed the chemistry of the oceans. They altered how carbon and oxygen moved between the atmosphere and the water. They fed microbial communities, giving them new energy and new opportunities for growth. And with these nutrient floods came a shift in the balance of life. Where once a few stable communities had ruled the seas, now there were waves of competition. Algae that could gather phosphorus more efficiently gained an advantage. Other organisms evolved tricks to store nutrients within their cells. New strategies emerged, small at first, but powerful in the long span of time. Minerals such as phosphorus do more than feed life, they also help it build. Phosphorus is a part of DNA and energy molecules. It is required to grow strong membranes and complex structures. With more of this element available, cells could expand their possibilities. They could build longer chains and more intricate forms. They could direct energy into new pathways. The biological machinery that once ran slowly now had reason to accelerate. This was the beginning of biological rewiring. Cells began to experiment with new chemical reactions. Some learned to take in iron and store it without poisoning themselves. Others developed ways to use phosphorus in different metabolic pathways. Gene networks shifted and reorganized themselves. New branches of life appeared in the fossil record, tiny and fragile, but unmistakable. The oceans no longer existed in perfect stillness. They were becoming places where resources flowed and changed, where one generation might live in scarcity and the next in abundance. These fluctuations did not just support more life, they encouraged cells to become more adaptive and more flexible. Each new nutrient pulse pushed evolution in one direction, then another. The rivers played a quiet role in this story. They did not move with sudden drama, they moved with steady patience. They carried the raw materials of change with them over long distances, weaving them into the fabric of the sea. Season after season, rainfall carved new channels, snowmelts added their flow, glaciers formed in distant highlands, and ground the bedrock beneath them into mineral-rich sediments. When these sediments reached the ocean, they settled into the water column. Microbes broke them apart and fed upon them. Organic matter drifted downward from the surface. Life began to form layers of its own, generations building upon what came before. In the quiet heart of this world, ecological upheaval was taking place. It was not violent or sudden. It was not easy to see in a single moment. But with every nutrient surge, the balance of the ocean shifted a little more. The boundaries between ecosystems softened. Communities that had once remained separate began to influence each other. This was not yet the great transformation that would come later. The oceans were still filled mostly with cells too small to be seen. The deep still held stretches of water that remained dark and oxygen poor. But the seeds of change had been planted. The nutrients that had been locked away for so long were now flowing freely. Rivers became the threads that connected the land and the sea. They tied together the cycles of rock and life. They delivered the building blocks that evolution had been waiting for. And as these rivers poured their minerals into the young oceans, the chemistry of the planet shifted just a little more. The sea became richer in potential. The story of life was beginning to move again. The oceans had been peaceful for a very long time. They were places of predictable rhythms where life grew slowly and changed even more slowly. Microbes shared space without much conflict. Nutrients were limited and stable. Energy flowed in simple patterns from sunlight to cell, then back into the water. For millions upon millions of years, this balance held. But balance is never permanent. Even the smallest shift in the rules of the world can create new winners and new losers. As nutrients began to move more freely through the oceans, and as oxygen reached deeper waters, the ancient equilibrium began to slip. It did not crumble in an instant. It unraveled a little at a time. Some microbes were the first to notice this change. They were the organisms best equipped to take advantage of new chemical possibilities. They could capture phosphorus more easily. They could store energy inside their cells for longer periods. They had already begun to experiment with new metabolic pathways. These subtle advantages started to matter. They allowed some species to grow more quickly and spread more widely. In places where nutrients surged, these microbes formed larger populations. They began to occupy more space in the water and on the seafloor. They did not share it politely, they took it. Once this happened, the old stability that had defined life for so long began to soften. The oceans became places where competition mattered. Competition had always existed in a quiet way, but now it gained strength. Microbes that had once lived side by side without conflict were forced to adapt. Some grew thicker, protective coatings to survive in crowded places. Others developed new enzymes that allowed them to digest nutrients that had once been inaccessible. Some spread into deeper waters that had recently gained faint traces of oxygen. A new pattern emerged. Wherever nutrients appeared, life responded in waves. Algae bloomed across the surface. Microbes multiplied in the water column. Organic matter drifted downward and fed even more organisms. The abundance of resources was no longer uniform. It came in pulses and pockets. The ocean was becoming patchy. In these patchy places, ecological imbalances took root. Some microbes became specialists. They thrived in high nutrient waters and grew in dense communities. They overwhelmed older species and pushed them into distant corners. These growing populations changed the chemistry of the ocean around them. They used up oxygen more quickly. They released new molecules into the water. They shifted the balance of minerals. Their actions were small on their own, but together they began to transform the world. With the rise of these new competitors, other species were forced to change as well. They became more flexible in where they lived. They evolved ways to survive with less light or less oxygen. They found niches where stronger competitors could not reach. These adaptations spread through populations and across generations. This was the beginning of cascading change. As the seas grew more crowded, the interactions between organisms became more complex. Microbes that had once been independent began to rely on each other. Some developed cooperative habits. They shared waste that others could use as food. They built slow-moving webs of exchange and dependency. Others took a more direct path. They began to steal resources from their neighbors. Some microbes produced toxins that reduced competition. These simple chemicals were early tools of survival and conflict. They were the first hints of the biological complexity that would one day lead to far more sophisticated strategies. The structure of the sea was shifting. Communities that had been stable for countless generations were now in motion. New organisms appeared in places where they had never existed. Old ones disappeared. The changes did not always happen quickly. They often took thousands of years, but in the vast history of life, these changes were meaningful. The ocean could no longer be described as calm. It had become a place of gentle turbulence. Nutrients rose and fell in cycles. Populations expanded and contracted. Microbial communities reassembled themselves again and again. Each shift allowed new possibilities to appear. Researchers today see the record of these changes in ancient sediments. They find variations in the layers of organic matter. They detect changes in the isotopic signatures of minerals. These signals reveal that the ocean had begun to experience fluctuations unlike anything from its earlier history. These were not chaotic or violent. They were patterns of growth and decline. In these imbalances, evolution found a new foothold. The pressure to adapt was no longer mild. It became a driving force. When one species gained a new advantage, others had to follow or retreat. These pressures encouraged innovation. They prepared life for the challenges that lay ahead. The oceans were learning to change, and life was learning to respond. The simplest cells were beginning to shape each other's destinies. And in this quiet contest for space and energy, the world was slowly being pushed toward greater complexity. For so long, the planet had moved in gentle rhythms. The seas shifted and mixed more freely. Nutrients flowed in new patterns. Microbial communities competed and adapted. Yet, through all of this, Earth's climate had remained steady. It was a world that preferred calm. Temperatures stayed within narrow boundaries. Weather patterns repeated themselves over unimaginable time. The atmosphere and oceans moved together like a slow conversation without raised voices or surprises. But no calm lasts forever. The same forces that had been building life's potential were also pushing the planet toward a different state. The tectonic shifts that opened new ocean basins and broke apart the ancient supercontinent did not stop. They continued in quiet but persistent motion. Volcanoes released gases into the air. Mountain ranges grew along fresh boundaries. Rivers fed the seas with minerals that changed the chemistry of the water and, in time, the air above it. These changes were subtle at first. They appeared as small shifts in temperature, slight changes in the way winds circulated, tiny variations in the amount of sunlight that reached the surface. But even the smallest change can lead to a new balance. The climate began to loosen from the steady path it had followed for nearly 1 billion years. The oceans responded first. Their currents, once predictable, began to shift course. Warm water moved farther from the equator. Cold water crept into places that had not felt it in ages. With each shift in temperature, new patterns of productivity formed. Algae bloomed where they had not before. Microbes adapted or retreated. The rhythm of the sea became more dynamic. These variations affected the atmosphere. Certain gases became more common, others declined. The air over the oceans began to hold more moisture in some regions and less in others. Storm patterns changed. Clouds formed in new places. Some areas became drier, others grew wetter. These were not yet dramatic transformations. They were hints, slow steps in a longer journey. Earth was learning to change again. The land began to feel the effects as well. As mountains continued to rise, they interrupted the flow of winds. They cast shadows across regions that had once been uniform in climate. They created new pathways for rivers. They forced air upward, cooling it and causing the first snows in areas that had not known them in countless cycles. Ice did not yet take hold, but there were early signs. The planet was preparing for something larger. The stability that once kept ecosystems in a state of quiet balance now began to erode. Variations in climate meant stress. For some organisms, this stress created opportunities. For others, it became a challenge they could not easily overcome. The competition that had been building in the oceans grew sharper. Life reacted to the new patterns of warmth and cold. Populations rose and fell in response. Environmental stress has a long memory. It changes not only the present, but the possibilities for the future. With each shift in temperature and each change in weather, the rules of survival changed as well. The oceans absorbed the new patterns and transmitted them into deeper waters. The atmosphere carried them across continents. This was the first time in a very long span that Earth experienced such subtle instability. It did not happen all at once. It was not a sudden crisis. It was a slow awakening. The planet was preparing to move away from the long and steady equilibrium that had defined the boring billion. The world had been still long enough. Energy had been gathering in quiet ways. Chemistry had begun to change beneath the surface. Scientists see the evidence of these early changes in ancient sediments. They find layers of minerals that reflect shifts in temperature and ice formation. They see isotopes that record the movement of water and air. They see the fingerprints of environmental stress written into the rocks. These clues reveal that the planet was entering a new phase. Glaciation did not arrive immediately, but the early signals of cooling were beginning to appear. Snow in high places, ice clinging to mountains, glaciers forming slowly in distant regions. These first signs were hints of what would one day become dramatic ice ages that wrapped the world in cold. Life did not respond with fear or hesitation. It adapted as it always had. Some organisms developed ways to survive in colder water. Others found comfort in deeper places where temperatures changed more slowly. Still others spread into newly available environments. The stress of a shifting climate encouraged new solutions. The longest calm period in Earth's history was ending. The planet was no longer a world of gentle sameness. It was becoming a world where change was possible again. The quiet rules of the past were beginning to dissolve. The signs were small but unmistakable. Earth was preparing to turn a new page in its story. As the world's climate loosened from its ancient stillness and ecosystems shifted into subtle motion, life was quietly building its most astonishing tools. The changes that had been unfolding in the oceans and atmosphere were shaping the environment from the outside. But something even more powerful was beginning from within. Cells that had once been simple, independent, and self-contained were learning entirely new ways of existing. These changes did not begin with large bodies or complex creatures. They began with microscopic instructions. They began in the language of genes. For countless generations, early eukaryotic cells had been experimenting with new methods of storing and using energy. Their mitochondria had grown more efficient, and their chloroplasts had become more versatile. Their internal membranes had become more specialized. But energy and structure alone were not enough to build complex organisms. Something else was required, something that lived deeper within the cell. Cells began to unlock the ability to communicate. This communication did not resemble words or signals as we understand them. It was a conversation held in molecules. Cells sent out chemical cues to their neighbors and received signals in return. These signals told them when to grow and when to rest, when to divide and when to remain still, when to stay alone and, for the first time, when to join with others. Alongside communication came adhesion. This was an unassuming but revolutionary change. Tiny proteins formed on the outside of cells. They acted like invisible hooks. These hooks allowed cells to attach to one another. A few cells could cling together and remain part of a group. They could form sheets or clusters. They could create tiny structures that were more resilient than any single cell could be. It may seem small, but this was the first step toward bodies. The ability to stick together meant cells could cooperate. One cell could take in nutrients while another performed a different task. Together, they could form simple layers that protected their inner members from harsh conditions. This was the earliest architecture of multicellularity. Communication and adhesion laid the foundation, but something else was forming as well. Cells were beginning to create energy networks that could support more than one cell at a time. They developed pathways that coordinated power and resources across small communities. These networks allowed cells to specialize, even if only slightly. One group could store energy. Another could build more complex internal machinery. These divisions of labor were the first hints of tissues. Under a microscope, these advancements would have been invisible at first. A cluster of cells drifting in ancient water, a few chemical signals exchanged across a membrane. A protein allowing one surface to cling gently to another. But within these subtle shifts lay the requirements for future innovation. Evolution was preparing to leap. The genes that controlled communication and adhesion became more refined. They spread through populations in waves. Those cells that could form weak bonds had an advantage. They could hold together in turbulent water. They could create films on rocks and sediments. They could colonize unstable environments more effectively than solitary cells. This was not yet the dawn of large organisms. No creatures swam through the water with shapes or limbs, but the essential instructions for such creatures were beginning to assemble. The technical requirements for building bodies were being written into the DNA of simple algae and protozoa. Scientists today study these genetic changes in modern descendants. They find genes that allow cells to communicate through chemical gradients. They find adhesion proteins that descend from ancient forms. They find the origins of the molecules that hold tissues together in every plant and animal. These discoveries reveal that multicellularity did not begin suddenly. It was not a single invention. It was a patient collection of steps. Each step was built on the one before it. Each was strengthened by environmental challenges and opportunities. Even as glaciers began to form on distant mountains and the climate grew less predictable, life was responding with new solutions. It was no longer enough to remain simple and independent. The world was changing, and so were the rules of survival. A cell that could communicate was more capable than a cell that could not. A cell that could attach to its neighbors could build something greater than itself. A cell that could share energy could survive in new environments. These innovations were like sparks waiting for fuel. Evolution did not rush. It did not hurry through this transformation. It allowed these changes to accumulate slowly, sometimes over millions of years. But the direction was clear. Life was preparing for something larger. The tiny clusters of cells drifting in the oceans held the blueprint for future forests, coral reefs, and animals. Everything that would one day crawl, swim, or breathe began in these simple exchanges of molecules. The genetic revolution was underway, and within it, the promise of bodies, tissues, organs, and organisms was quietly forming, layer by layer, instruction by instruction. The oceans had been places of patience and repetition for so long. Now they were places of preparation. The language of life was becoming more complex. The rules were shifting, and the first whispers of multicellularity were emerging from the depths of time. The oceans had been gathering momentum for a very long time. They had been absorbing the nutrients that rivers carried from distant continents. They had watched cells learn to communicate and join together. They had shifted with the changing climate and currents. Deep water had begun to receive oxygen for the first time in millions of years. Communities of microbes had grown more diverse. Competition had altered the balance of life. All of these changes were building quietly toward something new. Life was reaching a point where simplicity would no longer be enough. The story of this moment is written in stone. Ancient rocks hold the first clear signs of increased diversity. When scientists study sediments from this period, they find more fossil types than ever before. They see patterns that show life was expanding its possibilities. The shapes and structures of microscopic fossils became more varied. Some formed elaborate shells, others developed layered walls. A few show complex branching. These fossils look familiar in some ways and strange in others. They are reminders that evolution does not always move in a straight line. It experiments. It creates forms that appear briefly and then vanish. It tries ideas that will not always work, but each attempt adds to the path forward. Among these fossils are the first creatures that belong to groups we can recognize today. Early relatives of algae became more intricate. Protozoa formed new body shapes. Simple multicellular organisms began to organize themselves into small colonies. These fossils show that life was beginning to explore complexity more boldly than ever before. As this was happening, the oxygen in the oceans and atmosphere continued to rise. It did not increase steadily, it came in pulses. Sometimes it grew, then fell again, but each pulse brought Earth closer to a threshold it had been approaching for millions of years. Gradually, oxygen began accumulating in the deep water and across the surface. It reached levels that allowed cells to use energy more powerfully. It allowed more intricate metabolisms to flourish. With more oxygen, life could build itself differently. It could grow larger without suffocating. It could invest energy in structures that were not purely for survival. It could afford to experiment with tissues and shapes. Energy was no longer the strict limitation it once had been. The door to complexity was opening. The oceans of this time were not quiet anymore. They were full of subtle movement and transformation. In shallow waters, algae grew in dense communities. They formed carpets along the seafloor and floating mats on the surface. In deeper places, microbial life adapted to new conditions. Some species began to take advantage of the oxygen that reached down from above. Others found refuge in pockets where conditions remained low in oxygen but rich in nutrients. New ecological roles began to appear. There were still no predators with bodies and limbs, but there were organisms that fed in more deliberate ways. Some grazed on algae, others filtered particles from the water. These interactions created more ways for energy to flow through the ecosystem. Life was no longer simple. It was beginning to organize itself into networks. From this world came the first Precambrian forms that hint at the explosion of complexity that would soon follow. Fossils known as the Ediacaran biota appear in layers from this time. They are soft-bodied and delicate. They show shapes unlike anything living today. Some resemble fronds. Others look like discs or rippled cushions. Some seem like branching tubes. These shapes are varied and mysterious. They seem to defy familiar categories. These organisms were experiments in form. They were evidence that evolution was searching for ways to build larger bodies. They were not yet the animals that would one day dominate the seas, but they were the first step. They were proof that the ocean was ready to support complex life. The oxygen threshold that had constrained life for so long was finally being crossed. The atmosphere held more oxygen than at any point in the distant past. The deep waters had begun to share in this abundance. The increasing availability of oxygen made it possible for life to grow beyond the limits of single cells and small colonies. The oceans were still filled mostly with simple life, but the overall pattern had changed. Diversity was increasing. New structures were appearing. Forms that once would have vanished now had the energy to persist. The world was entering a stage where evolution had new tools and new opportunities. This was the world right before complexity exploded. It was a world of transition, a world with hints and promises of what was to come. A world where every ripple of oxygen and every surge of nutrients carried the possibility of new forms. The ocean was full of potential. The foundations had been laid. The conditions that life needed had finally come together. Change had become the rhythm of the planet again. The old barriers that had held life in simplicity were falling away, and beneath the surface, in communities too small to see, the next great era of evolution was rising. The oceans had carried the world through a long and peaceful age. They had been places of slow change and quiet stability where life experimented patiently with the tools that would one day transform it. For nearly a quarter of Earth's entire history, Evolution had moved at a pace that seemed almost still. The boring billion had been a time of building and preparation, a time when the planet held its breath. Now the silence was beginning to break. All the subtle changes that had been shaping the world for millions upon millions of years were starting to align. The oceans had grown richer in nutrients. Their deep waters had begun to take in oxygen. Microbes had learned to compete and cooperate and build new structures. Climate had shifted from long stillness into slow motion. Rivers carried the minerals of mountains into the sea. Tectonic forces pulled continents apart and reshaped coastlines. These changes were not separate events, they were threads of one great story, and now those threads were being woven together. For the first time since life had begun, the world held the conditions needed for complexity to spread. Oxygen levels reached a threshold that allowed more energy than ever before to flow through living cells. The deep ocean was no longer cut off from the surface. Nutrient cycles moved freely across the seas. The quiet chemistry of early Earth was becoming a vibrant network of reactions and possibilities. Life was no longer limited by the old boundaries. It was no longer held in place by the same lack of oxygen or the same shortage of mineral building blocks. It had the space to grow, to shift, to change. What had once been a world defined by simplicity was now beginning to press against the edges of its own potential. The fossil record shows this moment as a slow crescendo. Those strange and delicate Precambrian forms began to spread into more environments. The shapes of living things became more varied. Some organisms grew larger, others developed tissues and layers. A few even formed the earliest hints of internal structure. These were not yet creatures with muscles or bones or nervous systems, but they were far more complex than anything that had ever drifted in the sea before. The ocean itself seemed to respond. Currents shifted, temperature patterns continued to change, glaciers advanced and retreated in distant regions. Volcanic activity pulsed across the continents. These forces might have seemed harsh, but they served an important role. They stirred the planet, they circulated nutrients, they opened paths for evolution. For so long, life had existed within gentle boundaries. Now those boundaries were wider and more dynamic. The world was no longer quiet, it was waking up. The final environmental triggers were falling into place. The atmosphere held enough oxygen to support rapid metabolism. Minerals that had been locked in rock were now dissolved into the sea. Ecosystems had become complex enough for new interactions. Competition, cooperation, and symbiosis formed the beginnings of ecological webs. These changes did not mean the Cambrian explosion had begun yet. They meant the stage was set, the world was ready. The conditions that life had worked toward for nearly 1 billion years had finally been reached. Imagine the ocean at this moment. It is no longer a place defined purely by simplicity. It is filled with drifting colonies of algae and clusters of cells joined in delicate chains. It is filled with strange and soft bodies that move gently through the water. They feed in new ways. They share nutrients. They form communities on rocks and sediments. They have shapes that catch the light and vanish as they drift below the surface. These are the first hints of a world about to change. The silence that had held the planet for so long is beginning to fade. It does not disappear in a single moment. It disappears in gradual shifts, in small but steady pulses of energy. In the growth of tissues and the rise of oxygen, in the movements of continents and the weathering of stone, the world is entering a new era. The forces that held evolution still for so long now release it. The walls that kept life simple have thinned. The oceans are poised to become places of invention. Soon, Bodies will gain shape and motion. Creatures will grow mouths and muscles. Eyes will open for the first time. Predators and prey will begin a dance that will shape every future age. But not yet. This is the moment just before. The moment when Earth's great silence begins to break. The world stands on the edge of transformation. Everything is ready. Everything is aligned. And the long held breath of evolution is finally beginning to exhale. For a very long time, Earth moved at a softer pace. The seas held simple life that drifted and multiplied without interruption. The continents shifted with patience. The atmosphere changed in slow cycles. For nearly 1 billion years, the planet rested in a kind of balance. There were no forests, or animals, or predators. The oceans did not yet shimmer with familiar shapes. Instead, they nurtured small cells that learned the first rules of survival. It would be easy to look at that time and imagine stillness as a kind of emptiness. To think of the boring billion as an age when nothing happened, but the world was not waiting in failure, it was preparing. During that long quiet, the foundations of life were being woven layer by layer. The oceans were gathering oxygen in careful increments. Rocks were releasing nutrients that would someday feed entire ecosystems. Simple cells were perfecting the inner machinery that would allow them to grow more complex. They learned to store energy with greater efficiency. They learned to communicate. They learned to join together. These changes did not announce themselves with dramatic events. They unfolded slowly, hidden within the inner world of cells and the deep patterns of chemistry. Yet each small step brought life closer to what it would someday become. The quiet was not empty, it was full of preparation. The stillness allowed evolution to build carefully. It allowed the planet to find balance and reset its chemistry. It allowed living things to explore possibilities that would have been lost in a more chaotic world. Those ancient oceans were classrooms. The cells that lived there were students learning how to survive in a world that would one day demand much more of them. When the world finally shifted, it did so because of the groundwork laid during those silent ages. Nutrients began to flow more freely. Oxygen reached into deeper waters. Climate grew less predictable. Cells gathered the tools they needed to form bodies. All of these were the result of slow change. They were born from patience. The pause was not a pause at all. It was the deep breath before a long and wondrous exhale. Even today, the story of those ancient oceans is written in the rocks beneath our feet. It is recorded in fossils that show the first experiments with multicellularity. It is revealed in the chemistry that once controlled the world. It reminds us how slowly and carefully the planet works. It shows us that sometimes the most important transformations happen quietly. The great explosion of life that would one day follow was built on this foundation. Without those long ages of stability, the world might never have seen forests or fish or the first animals that walked onto land. It might never have seen the rise of creatures with bones and eyes and hearts. It might never have seen the beauty of living things that could think and feel and wonder. There is a calm power in slow change. There is beauty in a world that builds itself patiently. The earth did not rush forward. It allowed time to unfold. It let simple life stretch into new forms with gentle steps, and through those steps, complexity emerged. This is the quiet message of the boring billion. It was a time when the world was learning how to be ready, a time when the ingredients of life were being shaped with care, a time when small processes prepared the earth for everything that would come after. The story of that age reminds us that beginnings do not always look like beginnings. Sometimes they look like quiet seas and drifting cells. Sometimes they look like stillness. But within that stillness, the future was being shaped. Now take a breath and let your thoughts settle. Imagine the silent oceans of early Earth. Imagine the slow stirring of change. The world was not waiting in darkness. It was building the foundations of every living thing that would ever follow. Tonight, we rest in that understanding, in the beauty of slow transformation, in the patience of a planet that knew there was no need to hurry. And as we close this journey, we remember that even the quietest ages can carry the greatest potential.